Excuse me? Is anyone speaking? I can't hear anything.
Hi, the speaker is muted.
No sound.
Can we request that the speaker unmute their microphone for virtual attendees?
Okay, cool. I think this splitting screen causes sort of problem. Let's maybe do it mirroring better.
Mirroring how? I mean, it's okay. You can just go. Otherwise, we're going to be very late. Thank you. Let me just. Only 1 second, because I don't know where my pointer is. Dimitro, what is the second screen? I cannot see the pointer. Oh, here, I think I'm here. Okay, okay, good. Sorry, this setup is really complicated. Okay, now I should be back on track. Thank you, and apologies. So yeah, some metrics were heavily saturated very early on this data set, but the most interesting thing is that there was a huge gap between what you would call traditional descriptors and more modern descriptors, and this is a bit surprising. This is something that we saw when I was working on a paper with a colleague, with Kwang, a co-organizer of this workshop. So we were working on LIFT, which became the first paper that was jointly learning the three parts of the classical descriptor, local feature pipeline, which is the key point detector, the orientation detector, and the descriptor. And what we saw is that we obtained state-of-the-art performance. So cool, you have a paper, but at the same time, SIFT was doing actually quite well. And many of the supposedly state-of-the-art papers in the middle of these plots were not doing so well. So, you know, where does this huge gap that you see between the last evaluation and this evaluation come from? There's not a lot of data sets that can be actually used to evaluate this in practice. So for instance, the two data sets that are still kind of in use or very much in use, one is HPatches, which is, it was initially a data set that was meant to also evaluate patch classification performance. It also published the whole images, and that's what's being used mostly nowadays. It has two types of sequences, which are showing only illumination changes or only viewpoint changes. It also uses intermediate metrics, and it has some limitations in the sense of, you know, this is the kind of change that you can expect with these images. It's mostly just static scene that you see from different viewpoints with a lot of texture, or just drastic changes in illumination with no changes in viewpoint. Another data set that is still used is the ATH Colmap benchmark, which is interesting in that it's very large scale. It targets structure from motion, but there is no ground truth. So the only thing that you can do is measure reconstruction statistics, such as projection error, or how many points and how many observations they have, right? Which is interesting, but it's not exactly going to tell you which method is better in this setting. So our proposal was to try to address this gap or this void with an open challenge. We have run it every year since 2019. It's the basis of a benchmark that we published. It's available on GitHub and a journal paper in IJCV. I want to say that there's a few more resources now, mostly visuallocalization.net has a number of data sets that can be used and tasks can be used for relocalization. And there are similar evaluations as the one that I'm presenting here on a data set called Megadepth. So what is changing on this year's workshop? This is the first post-pandemic, let's say post-pandemic in quotes, hybrid format. CVPR is not providing a lot of support, as we saw now. We had a lot of issues the first 10 minutes. I hope that they are mostly resolved now. We have 7 speakers joining in person and 7 joining virtually. So hoping that everything will work out. We have 7 workshop papers, which is a lot more than we had in previous editions, and 5 challenge talks. The schedule is very tight, and it's even tighter because we started late. So I'll ask everyone to please save the questions for the end, or just ask them on Zoom chat, and we'll relay them to the speakers. Brief history of the challenge. 2019 was the first edition, and we've had multiple challenges other than the one that I'm mostly talking about, such as Silva and Simulate Match. That was from a colleague who's not being able to organize a challenge this time, so I'll just talk about the other one. In 2019, winners used mostly learned patch descriptors, so basically like SIFT, with a learned patch descriptor. In 2020, it was a really nice year, I think, because out of the 4 winners, we had 3 that were introducing novel papers, such as superglue, Adalam, or disk. So I think that was actually kind of like what we were hoping the challenge would become. And in 2021, it was a bit different. So instead of trying to make it deeper. We just made it wider, and we tripled the number of data sets from 1 to 3. In the top performance, we're having mostly like more engineered solutions, right? And the challenge got significant, pretty much the same number of submissions, which was okay because it was much shorter due to the overhead in adding all of this data. For 2022. This is something that we wanted to do for a long time, and this year we succeeded. We moved the challenge to Kaggle, and we actually have a nice prize. So we have $10,000 for the winner. This challenge is sponsored by Google. We'll have more details at around 4. I just wanted to briefly talk about, did it work out? So these are the number of participants and submissions that we had the last 3 years, which was between 28, 25 teams the past couple years and about 100 submissions. So this is where we are this year. So obviously it worked quite well. We have about 25 times the number of teams and about 150 times the number of submissions. So that was quite good. Very brief recap about how Kaggle works. We'll talk about it more later, but it's a code competition. So basically just write whatever code you want on a Jupyter notebook on Python, and you submit it on submit for offline evaluation on a private test set that you cannot access. This makes it very difficult to cheat, which is a problem in this kind of competition because you can get very good poses, which is the goal of the competition, but just annotating a few points manually, right? So this is actually a big concern. It has a fixed compute budget, so you can just do whatever you want for like 9 hours, and it allows for quickly iterating with different solutions, which is very nice. It also enabled a lot of different people to participate, so from academia, from industry, and even some complete freelancers and people who had no experience with this kind of problem, which I think is really cool. Cool. At the same time, this was a learning process, and we learned some lessons that we'll talk about it if we have time at the end. So this is going to be the schedule again. We'll move on to the invited talks. So we'll start with Tom Malishevich, who's now at Meta. Tom, can we check if you are here? Can you?
Yeah, can you guys hear me?
Yes, we can hear you.
But
How to plug the audio to do it?
it's a good question.
Yes. Tom, we are trying to figure it out. Give us a minute.
Okay, no problem.
We hear you, but not anyone, no one else, I guess, hears you.
How to connect this thing? Okay, can we just put it here? Say something.
All right, can you guys hear me still?
Okay, we have sound output.
Input, output.
It's later. Say something now.
Okay, how about now?
This not. Oh wait, there's also a separate thing in Zoom. Okay. There is in Zoom. No, it's wait, it's yes. Try something, Tom.
Okay, how is it now? I can see the coffee break and
Yes,
toaster
great.
session slide.
Does this sound good enough? Yes,
It's-
that's what we
Wait,
have.
we can have. Okay, is it maximum? Tom, continue saying something, please.
Okay, yeah, whenever you guys let me know, I have my slides ready to go. So after we pass all the checks, I can begin.
Does it come through the speaker on the,
Yes.
on the projector? That's what we have. Okay.
Else maybe we can look at the speakers, yeah. So you set up
Wherever.
the input correctly. So again, mute, down, and now
External headphones. What is? Okay, external headphones. Just say something again.
Okay, how is
Tom?
it sounding now?
No. So it's the best we can have.
Okay.
From
There's
that.
no speakers, right? I only see
There's no speakers.
like there's nothing.
Yes. Okay, so you can
Oh, there's no
share.
speakers actually. I don't know.
You can share screen,
Okay,
but its sound is, I think, good for audience, but bad for local audience. Okay.
do you guys see my slides?
Oh,
Eh,
you can show it. Yeah.
Oh, wait. Where is Zoom? Okay, is Zoom crashed? No. So it's
Here.
it's here, and it's not. Sorry, I'm really sorry. Okay, one minute. I think it would be. It was so stupid idea to remove the mirroring. I'll fix this first.
We need a few minutes. Sorry.
Yes. I don't remember who was that guy who advised it, but it was very bad thing. Great. So it's done. Zoom here. Okay. Not. Okay, now we can see your screen. No, but there is no good output.
So this is the.
Yeah, so this is the output for there.
But that doesn't work. That doesn't make any sense. That's nothing.
I mean, is there any other?
Sorry, what? Okay, that's
Point
maybe the-
mic to the laptop.
That's the best we can do.
Incredible idea. So yes. MacBook Air speakers. Okay, Tom, say something now.
Okay, how is the sound working now for you guys? Is
You're
the sound okay?
trying to mic at you.
Folks in the chat are saying the sound is good for them. That's in the Zoom chat.
Wait, not yet. It's to be through, but there's going to create echo, isn't it?
Should work. Okay, say something now.
Okay, let's do our last check and see how it works so far.
This actually works. Okay, thank you. So yeah, sorry again, complicated technology. It's my pleasure to introduce Tomasz Milicevic. Tom did his PhD at Carnegie Mellon under Elia Shafros and a postdoc at MIT with Antonio Torralba. In our field, he's very well known for his work at Magic Leap. He was principal engineer for several years, during which he co-authored 2 seminal papers in image matching, which is the topic of this workshop that most of you probably know, which are superpoint and superglue. This is what he'll be telling us about today. And also, these are interestingly some of the methods that are used by almost all of the participants in the challenge. So remains very much in use. He's now at Meta Reality Labs. Tom?
All right, thanks for the introduction, everyone. Today, I'm here to talk about those 2 seminal papers, Superpoint and Superglue. But what I will do for the first time is I'm gonna take a look.
Give us 1 second, sorry. We need to fix one thing. So
Here,
just address it. Oh, it's mirroring now. Perfect.
Yes.
So full screen?
Yes.
How do you full screen?
That's I think
So
there's
that's
a-
what we can do. Yeah, hide that.
I don't know. So why this participants are showing?
Standard.
Yes.
Yeah,
Okay.
good.
Great.
Okay. Now we are actually good. Please go. Apologies.
All right. Okay, great. Everybody's saying they can hear me fine. People can see me, they can see my slides. Excellent. So the new thing today is going to be, I'm going to be highlighting the lessons learned from those two projects. Some of the things we designed at first, some of the surprising things we learned, and I'm going to offer a couple of meta lessons at the end that kind of summarize some of the key strategies. And I want to sort of empower the next generation of researchers to think a little bit outside of the box when they are working on their own key work. As mentioned before, I am now at Meta Reality Labs. I'm a research scientist manager there within the Surreal group in the Pacific Northwest in the Seattle area. You will hear today, later, some of the work done by some of the other Meta Reality Labs researchers and interns. Excellent. Yeah, so Superpoint and Superglue were given birth to thinking about visual SLAM, thinking about all-day perception, thinking about what it's like to make machines move through space, autonomous driving, mixed reality, autonomous robots. However, it was mixed reality that was the key application, the one of wearing glasses that let you see part of the real world, part of the environment around you, and adding digital objects. So this work here is going to be work done from my Magic Leap phase, where I was there for 5 years, as mentioned earlier, a principal engineer there. And I will mention some of the key people whose lives I influenced by working on these projects. So today I'm going to give the quick overview of Superpoint just for comprehensiveness, so everybody can come in and participate in this talk without prior knowledge. I will also talk about Superglue, and what's new is the lessons learned section. I'm going to, after Superpoint, mention a couple of lessons about Superpoint. Same thing with the Superglue section. And then finally, I'm going to wrap up with the meta lessons learned. And those are designed for young researchers to just be aware what might happen after their PhD and keep their eyes on the bigger prize out there. So yeah, let's take a look at sort of Superpoint. What is it? What it's sort of all about? Now, when I started my PhD a long time ago, everybody was still talking about SIFT. That was 2005. And I kept thinking, man, if SIFT is so famous, so popular, even decades later, let's keep doing the same recipe. There's something about points matching them that's here to last for a long time. Deep learning was new. Let's design convnets to replace SIFT. We started working with this following paradigm. There's the front end part of Visual SLAM and the back end part of Visual SLAM. The front end extracts the features, the key interest points, and the back end will do the bundle adjustment and the 3D estimation from the 2D features. Superpoint is a deep SLAM front end. At the time that we designed it, we were using a very simple convnet. This was still before ResNet. This was a VGG-based backbone. And then we wanted to have multiple heads, one for detecting the key point 2D locations and one for detecting the key point descriptors. This work kind of is simple. It's one of the reasons why the world liked it. We had a hard time publishing this work at the main CVPR venue. We decided that the workshop on Visual SLAM, the deep learning for Visual SLAM workshop, would be good enough. It actually ended up working in our favor, that this workshop brought all the deep learning and Visual SLAM experts together. We really had an awesome audience to show off this work for the first time. A simple lesson there is, if your work doesn't get into the main conference, keep looking for a venue where your work might be received. Don't necessarily abandon something if you believe in it. Yeah, so Superpoint is points and descriptors are computed jointly. No patches are extracted. VGG-like backbone. We did design it for real-time processing on a GPU. At the time of creation for Superpoint, we wanted to keep the backbone lean. We were thinking really about running this on a device, on a companion compute device, but not something that would just have academic value by being an overly large and fat network. Yeah, so the front end is going to be the super point, and the back end is just something done by a separate algorithm, typically bundle adjustment, for doing the full visual SLAM pipeline. In terms of training superpoint, there were certain key difficulties and certain key insights, and some of the lessons learned are going to come from the how to train superpoint section. So to set up the training, we use the MS COCO data set of images. We would warp the images using homographies, create correspondences between points. That's going to be a separate network I'll talk about where they came from. Relatively simple Siamese training, contrastive loss. Everything is pretty textbook at this point. The key question, though, is where do the key points come from? That's not something you can just ask human labelers to label the key points. So these are MS COCO images. And yeah, if you send them to Amazon Mechanical Turk and tell people to label interest points, they're not going to come up with something that's necessarily coherent and makes sense. And that's because interest points are an entity created by machine vision researchers for the task of comparing images and matching them. It's just too hard for humans to do. So we followed a self-supervised training recipe. We first started with a synthetic world, and we had a synthetic shapes renderer. This is a Python renderer that just generates simple shapes. And then once we train to detect the corners of those simple shapes, then we project everything to MS COCO, where there are no interest point labels. And MS COCO has a lot of images, but it's not the kind of data set you would think a visual SLAM researcher would ever use, because these are disconnected snapshots of reality. They're not videos. There is no 3D associated with those images. We had to invent something called homographic adaptation to project from one world to another. But the self-supervised theme, still a very popular one today. I'm glad at that time we saw the promise of self-supervised learning and included this as a first-order citizen in that work. So the synthetic training was relatively simple, but it involved lots of heavy noise being applied to the images. Here's some examples of what the synthetic training was able to generate for creating that core interest point detector. We had an earlier version of superpoint that we called magic point, which was just the interest point detection bit. That work we only got out on archive. I do believe we had attempted several times to publish it, but it was something that wasn't being received very well. People were like, oh, you're doing something old. This doesn't feel like new research. However, it was a great starting point for us. We did evaluations. It convinced us internally that magic point were much better systems for detecting corners compared to all the classical techniques. Homographic adaptation was then the self-supervised thing we had to invent to get everything working on real images. We start with an unlabeled input image. We do the synthetic warping of the image, generate many different versions, warped under different homographies, run the magic point detector, warp the images back, and then aggregate the points. And we observed we were able to detect a superset of the points as a superset relative to their individual images. That's where the name superpoint came from, the fact that we could detect a superset of points. Now, 3D generalizability of superpoint was something that kind of came out for free. We trained and evaluated on planar scenes, but then when we applied it to video sequences using a simple connect the dots nearest neighbor matching algorithm, we found that it worked surprisingly well on a large diversity of images. In fact, it seemed to work pretty well on just about any application. That's because it was trained on COCO with a lot of noise. It really got to see a very diverse world. This isn't something that just works on Kitty, it doesn't work on other data sets. It worked a little bit everywhere. And that was one of the key things that made the technique successful. People have used Superpoint in lots of interesting applications, and it's always a great baseline. It's not the easiest to beat, but if you do push on your own system, your own application, you can usually beat it. But Superpoint is a embarrassingly powerful baseline for all point-related tasks. So then we released our super point at the workshop. That was kind of a big success because the actual release was essentially 2 files, the pre-trained model in PyTorch and a simple demo script that would show you how to run it. And then OpenCV in Python was doing a lot of the heavy lifting, loading image streams, things like that. But simplicity was key. So let's take a look at some of those lessons learned, things that I might have talked to you if we had sort of dinner at a conference together, but not something I would have presented before. Okay, so let's take a look at the first lesson learned. What did not work? So the one thing that didn't work is this whole era of research that we did right before Superpoint. We tried to use convnets to directly estimate the relative pose between images. That did not work for us. There were key papers, I believe called PoseNet from ICCV 2015 that showed there is some promise in having deep learning convnets just figure out the whole pose problem. But something was fishy when we tried working on this. It was very easy to tell that the convnet could take a look at a pair of images and figure out if the motion is to the left or to the right, or you're going forwards or going backwards. But getting a precise 6DOF relative pose was very hard. It really didn't work. We spent kind of a lot of time working there. We eventually had to abandon this direct relative pose estimation. And I came to the realization that convnets were very tied to the image plane. And relative poses are much more high-level quantities that describe the configuration of cameras. They're not really tied to an individual set of pixels. So the second lesson was, well, let's leverage what we know already. And I had known quite a lot about object detection from my work on the exemplar SVM, on hog-based techniques that I had developed during my PhD. Now, hog techniques, the formal part models, they seemed like a world long time ago when deep learning came, but it was really only a couple of years after the deep learning revolution happened that we were working on Superpoint. So the key was like, well, object detection can detect objects in the image plane. Let's build a point detector that detects points much like an object detector would detect objects. And then we realized, well, that's what's going to help us build a Superpoint. So the lesson here is you might utilize skills in one domain when you go into a new domain. And in this case, the new domain was visual SLAM, and the old domain was object detection. And it worked quite well to be able to take techniques from one domain and bring them to the other. Third is we used MS Coco for training. And at first, we had a lot of resistance from the in-house teams that were collecting their own data at Magic Leap. They said, why don't you use our data that we collected? Well, there were several issues with that data. And ultimately, we realized if we used in-house data, it would be hard for us to write a paper about Superpoint. It would be very difficult for us to release the data set that's created in-house by VC-backed sort of company. The data had a lot of things that needed to be clean. It was great for internal use, but not something we could have ever really disclosed in a paper how we collected that data. And in addition, by using MS Coco, it made Superpoint work on a more diverse world than we had anticipated. And that's what made the technique last a lot longer time. Now, the benefit of using the public data is that more people trusted the technique, that we could disclose the whole recipe. We never gave out the synthetic shapes renderer, but people could kind of create their own by looking at several example pictures. That's not the most difficult part. So I think this was a decision that at first I wasn't sure was the right one or the wrong one, but many years later, I think it was the right decision. We avoided using an in-house data set that we had concerns with. We used a large-scale, publicly known data set that made it easier for releasing ultimately the paper, describing the technique, and convincing the research community that it works. I think that was the right decision at that time. but it was hard to tell when we had to come up with this. And the last lesson learned is that simple synthetic shape renderer that I had described earlier showed some pictures that performed on-the-fly training data generation using a simple OpenCV renderer in Python. It really helped us get off the ground. It essentially meant that our training scripts did not have to rely on data. So anywhere we had a GPU, we could simply send the Python program. Once it has PyTorch up and running, it's accessing the GPU, it just starts generating training data, and we can start debugging the training pipeline. We can start perfecting it. We don't have to worry about, is the data loading slow? Is it fast? Where are the images? Are they allowed to be on this server? Are they allowed to be on that server? All those questions went away. It was really a great starting point to get our first point detectors up and running off the ground. Now I'm going to jump into the second part, talking about that second key paper, the super glue one. Now this paper came out in CVPR 2020, just 2 years ago, and it was all about matching local features. It was about learning how to solve the correspondence problem. This paper was done by Paul Edouard Sarlin, who was an intern at the time in my group. I'm going to describe in some of the lessons learned, some of the backstory behind Paul that will help convince everybody what really it takes to write a great paper in industry. All right, so let's go into this little section, do a quick brief recap of superglue before we go into the lessons learned. So the title of the paper was Learning Feature Matching with Graph Neural Networks. And this was done with Paul, who did this work as a part of his master's degree requirements at ETH Zurich. Superglue is a graph neural network and an optimal transport procedure. As input comes an image pair, the local features, which were mostly superpoints, also we tried this with SIFT also, come in as input. And then the graph neural network alternates between self-attention and cross-attention, letting the features communicate, does that for many, many layers, and then it ultimately creates matches between the features. That goes into back-end optimizer like bundle adjustment to do the estimation of 3D. Now, superglue worked really well for extreme wide baseline matching. It also works in real time on a GPU. We trained separate models for indoor and outdoor tasks. We did a pretty large scale evaluation. And that's how we ended up being on the radar for this image matching challenge workshop. And the goal of superglue is to be better than motion guided matching without any motion model at all. Before we had superglue up and running, we were using a lot of odometry cues to help match superpoints. But we found out that we were actually injecting heuristics about motion, about geometry into our C++ and Python programs. For superglue, we want to take a step back and say, let the machine learning system figure out how to do all the hard stuff. Superglue is a graph neural network with attention. And as we know now, attention is a big thing. We were inspired quite a lot by the work on transformers. At the time of superglue in our local Magic Leap reading group, we spent a lot of time talking about transformers, language models, attention. We were really getting our brains, wet with these new ideas. And then superglue kind of came out of those study sessions. So the graph neural network encodes contextual cues and priors, it reasons about the 3D scene. And then the Sinkhorn algorithm solves the partial assignment problem just by creating a compatibility score matrix and performing alternations of row and column normalization, ultimately outputting a partial assignment. It's a partial assignment because a feature in one image could be not visible in the second image. That's why it's sort of partial, but that's sort of key to make it work in a lot of scenarios. And the key thing to remember here is that superglue requires both sets of local features. as input, 2 images come in. This is quite different than what we were doing with SuperPoint, where a single image comes in, you compute all the features, you can cache them, and then when you have basically a large collection of images, you just do the SuperPoint extraction once, and then you can just match everything. Here, doesn't scale as well with sort of superglue. But in the lessons learned, I'm going to talk a little bit more about this requirement of both sets of local features, what it meant for us and why we decided to go that route. So here are some visualizations of SuperPoint and nearest neighbor on the left showing matches, and then SuperPoint and superglue on the right. Higher density of green lines means more correct matches. So on the right, we're seeing more correct matches and fewer mismatches, and mismatches are the red lines. One of the key things here is look at the floor, look at the bathroom floor in the top sequence. The local features really hard to disambiguate because they're just tiles. But there's something about superglue that's able to allow communication across all the features. It's able to disambiguate those matches by using all the context. That's really the power of the graph neural network. We applied this to outdoor data. We also applied it to indoor data. And in the evaluations, we found that the superglue on top of SuperPoint was a lot better than just SuperPoint. And when we repeated the same thing with SIFT, we found that adding superglue to SIFT was also better than SIFT. In our scenario, the SuperPoint and superglue was better than SIFT and superglue, but there are still certain scenarios where SIFT is sort of amazing. Certain applications, it's hard to move away from SIFT, especially if that design decision has been made years ago. But we did see large improvements, very strong empirical results. We also released the demo. People could go ahead and download the pre-trained network and apply it for their own problems. It works relatively fast on a single GPU. With today's even beefier GPUs, just going to get faster for you. If you go online and download the demo, you can get something, you can just play with something like this. You get the superglue demo where you freeze one image and then you move your webcam around and you can try to break it, try to play with it, see what happens when you turn your lights on and off, try out checkerboard patterns, unique patterns, rotate things around. Really a great kind of demo for yourself, especially if you're starting out. You want to see how an amazing point matching demo would look like. You can just get this really running in a few minutes. Yeah, so superglue, again, we evaluated it at the image matching local features and beyond challenge. We did a lot of other tasks. We won a lot of prizes at CVPR 2020, different challenges that really helped convince the research community that things were working. This paper had a very strong empirical results. Again, this is something that would not have been possible if Paul had only done a short internship. Paul had a 6+ month internship where we knew that the work was going to have to come out as a paper. He's working on his master's. We needed to have strong empirical results. Couldn't be just an idea. Couldn't be just something we think of and we patent. No, it had to be something we convince a broader community of its merits. So let's take a look at some of those superglue lessons learned. And I was just hinting at this. Experienced candidates are key to internship success. In this case, Paul Sarlin had the key background even before starting this internship. And let me tell you some of the key things. First, Paul showed up on my radar because when he started his master's, he had tried to recreate the SuperPoint training recipe. And there was a GitHub repo from Paul and his colleague on trying to get SuperPoint up and running. In fact, that repository was online a few months before we released our SuperPoint actual demo. Their version might have not been as good, but because Paul did that work, he was on my radar. And he also then started his first internship at Magic Leap Zurich, which was not with me in the Silicon Valley group, but that helped him get into the organization. I got a chance to meet him. Then it was very easy to get Paul to move to Silicon Valley, San Francisco area for that longer internship. So all those key works he had done before. And we also had to extend the internship just to get this awesome paper out. I'm mentioning this is because some people have unreasonable expectations for what can happen in a 3-month internship. Again, 3 months is a very short amount of time. I don't want people to do internships and feel bad if they can't write their superglue-like paper. Paul was essentially preparing for the superglue work for about a year or so with all these other internships, that superglue experience. So that's a little bit of caution for everybody. Just don't feel bad if you don't get a paper out in a 3-month industrial internship. And another thing, if you like somebody's work, try to get a GitHub repo of it up and running. Who knows, maybe they'll invite you to do an internship with them. It worked for Paul. I think that's a key thing that he did that just put him on the radar. I encourage everybody to just find those papers they love and build implementations, put them online and see what happens. So let's look at another lesson, moving away from practical systems. Now, we decided to move away from this computed descriptors paradigm, and we made the input to the network 2 images. We knew at that time that computationally this was a lot more expensive. To actually do this for image relocalization, one of those loop closure tasks in Visual SLAM, superglue is not really maybe the best way to go if you're building edge devices that have to do a lot of the Visual SLAM. Nevertheless, we decided we're going to go that route. We're going to get an excellent paper out with Paul. We're going to do great science on it. But we might not necessarily be building something that's going to go into our products this year. That was hard for me to sort of swallow and realize that the internship was going to go that route. But look, you have to choose. Are you going to please the engineering forces of your organization, or are you going to scientifically disseminate something amazing? It's important to not do a little bit of both. You don't want to have a little bit of internal impact and write a little cute paper. It's probably better to have big internal impact, get rehired, think about your career within the company, or build an excellent paper where scientifically you get a lot of kudos, a lot of respect, a lot of visibility. So we decided to pivot towards this working on great science route. And about in the middle of that superglue internship, I had realized that's where we're going. I said, you know what? There's no looking back. Let's not worry about our engineering friends. Maybe this won't fit inside the Magic Leap devices in the near future, but that's okay. Let's just do amazing science. And I think looking back, that was a right decision to make, but it's very specific to the project that you're working on and how far you can get in the middle of the project. So let's now wrap up and look at some of the meta lessons learned. What did I kind of learn as an individual that I can teach you about these projects? So the first one is about reinventing yourself. And I say this because I had to reinvent myself several times after my PhD. And the SuperPoint and the superglue are essentially that for me. They're the kind of works that I had to do to convince myself and the world that I could do independent, great scientific work without a PhD advisor. This SuperPoint and superglue happened in that decade-long chapter after my PhD. As I mentioned, I had done object detection work during my PhD with Alyosha Efros, but he wasn't here for this chapter of my life. And this chapter involved a lot of deep learning. I had to reinvent myself. I had to abandon a small startup I had that invested in pre-deep learning techniques. I had to just say, you know what, this was a small company that was becoming a consulting company. I had to say goodbye to that. You're not scaling. I had to join a VC-backed company to be a full-time deep learning researcher so that I could learn. I couldn't have a consulting company and be learning deep learning on my nights and weekends. I had to be doing it as a full-time job. So I had to join Magic Leap. But then SuperPoint and superglue were those successful chapters that convinced me that that work had significance and will continue on having significance. Don't be afraid to reinvent yourself. You'll have to do it. Probably every decade, there'll be something new. You'll have to just be humble, learn it, and do it. But it's key to think about who you're going to bring along for this adventure. When you think about your success post-PhD, think about helping to create careers. Your post-PhD impact will influence the young researchers you work with. Some of the really young people will continue to pursue a PhD. Some will get high-tech jobs, but you will feel proud of, quote unquote, your students, just like when you were a PhD student and you were very proud of your, quote unquote, first author papers. So that's going to shift in the kind of post-PhD, where the people you influence is going to be like the papers that you wrote. And the last thing is, the more you publish, the more people know of your work. I am really proud of those 2 chapters of my life, the Superpoint and Superglue. I still meet people on a regular basis that know of me because of that work. And we have something exciting to talk about. Still meet surreal interns who know me from that work. And it's just great to have a coffee with them and chat. By giving talks, you're going to meet future collaborators, future employees, future employers, etc. And it's not always easy to publish papers while in industry. People have to think about lots of reasons. Some key insights you want to hide from competition. Sometimes you'll have data that your algorithms touched that is sensitive, and you don't want to release sort of something that, from a privacy standpoint, you're going to regret. A lot more to think about when publishing a paper in industry. In my general opinion, is it's worth it, but it's not always possible. Don't think every work you do in industry can and should be published. But I think every 1 to 2 years, if you are a researcher in industry, you should still have something nice that you can publish. You can talk about, you can give talks about, just meet other folks. And with that, I think I only took up about 30 minutes today. I want to thank the key people who, as of recently, it was Daniel DeTone. He was the first author on the Superpoint chapter. Paul Edward Sarlin was the first author on the Superglue. As of recently, both Daniel and Paul and myself have been at Meta, Paul as an intern, and Daniel and myself as full-time researchers. It's been great having meetings again with Daniel and Paul, just like we did in the Magic Leap phase. And even though our companies changed, we still have a great working relationship. I still continue advising Paul as much time as I have. I have regular syncs with Daniel. We continue talking about this Deep Slam vision, although it looks different now at Surreal, at Reality Labs than it did at Magic Leap. It's still exciting to know that the people whose lives I had a chance to influence are still in the brainstorming room. We still get to tap into our brains, enjoy our conversations. And I look forward to not only seeing where Daniel and Paul end up, by having another next generation of young researchers come to my team or the neighboring teams, working closely and seeing where those junior scientists can become. And with that, I want to conclude my talk. Thank everybody for listening to my lessons learned on Superpoint and Superglue Talk. And with that, I have a few minutes to take a couple of questions. Thanks, everyone.
He would not hear it.
I think he would, because it's the same. Yeah, it's fine. Could you hear me talk, Tom? Just
I
a sec.
can. I can hear.
Before that, let me try again. I'll ask a question from the other mic. Can you hear me now, Tom?
It's a little slow, but I can hear. Try again.
I can just do it from this mic. So we have a question from chat, which is from Fichue. Do you think it's possible in the future that we can recover camera pose directly from images by using CNNs or something else without explicit correspondences? I think it is a worthy problem to keep revisiting every few years. Just because I did it in 2015, 2016, which really feels like a long time ago, and if it didn't work for me, it doesn't mean it won't work if somebody else sort of tries it. Certain key problems you have to keep trying. I don't think CNNs are the right thing.
But I think in today's world, we have so much happening with the vision transformers, a lot of new techniques. I think somewhere in the space of new deep learning techniques, people should try this out again, but they shouldn't not necessarily expect AlexNet, VGG style, kind of old-fashioned networks to be the right thing for getting camera poses directly.
Sounds good. Thanks, Tom. So in the interest of time, since we are running still decently well, since Tom was really fast, thank you, but a bit late, we'll move on to the second speaker. Thank you, Tom.
All right, thanks everyone.
Sergey?
Okay, so hello. Let me introduce the second speaker. It's Aleš Rabalik. He's from Capturing Reality, one of the leading companies in 3D structure from motion and actual asset building. And he is a lead engineer of the let's say, flagship product. And I think it's a very nice counterpoint compared to the previous talk, which was about how to do research and science in a company. And here, this is about making a product great. So I think two talks from companies with slight different points. So Aleš is a graduate from the Czech Technical University. And since he finished in both graphics and vision, tried to find a place which would nicely use both these skills, he moved to the company and has been there ever since. So Aleš, the floor is yours.
Thank you for the introduction.
So I'm just blowing mine. Should be okay.
This is okay? Okay, thank you for the introduction. Thank you for having me. Hello, this is large-scale 3D reconstruction. As was mentioned, my name is Aleš Rabalik. I am a lead developer at Capturing Reality, which is part of Epic Games. We are a small company based in Bratislava, Slovakia, and we specialize in 3D reconstruction software. Our main product is called Reality Capture. In this talk, I will cover the successes of deploying reality capture at a large scale, the limitation and future challenges of 3D reconstruction in general, and finally, I will cover some research topics and related open problems that are needed to be tackled to overcome these future challenges. Before I start, please understand that while I'll be completely honest about what our software can and cannot do, I cannot give you any specifics on the method used in our software. Okay, let me get rid of this interface now. Seems like it works. Come on. Okay, so what are the successes? Firstly, we have developed a general application, which is evidenced by the range of industries that use it. For example, in architecture, building interiors and exteriors are being scanned for visualization and interior planning. Works of art are being scanned for preservation, as well as presentation in virtual museum exhibits. Land is being surveyed from ground and air to create maps and to analyze the terrain. The entertainment industry is leveraging our software to do visual effects and to create virtual characters and environments. But it's not just the experts in various industries. Increasingly, 3D reconstruction is being done at home and on budget. And we have to consider these customers going forward. It should be noted that apart from the traditional outputs of 3D reconstructions, that being camera poses and calibration and shape typically in the form of a mesh. Our customers require, and we provide, appearance in the form of a color texture map. A significant success is that our processing time scales almost linearly with the amount of input data. As a quick demonstration, I took a publicly available data set and processed it multiple times with a varying amount of input data. As you can see, doubling the amount of input data roughly doubles the processing time. Our customers leverage this scalability to process extremely large data sets. We have seen image counts up to 300,000 input images. We've seen ultra high resolution images up to 151 megapixel. The total pixel count of the project has sometimes exceeded 3 trillion pixels, and the output sizes are not negligible either, with the output triangle count exceeding 8 billion triangles in some cases. To ensure the performance and scalability, we impose restrictions on the algorithms that we can use. We require that these algorithms are scalable, that is, their asymptotic complexity is linear or almost linear. We cannot guarantee that all of the data fits into memory. Thus, we require that the algorithms are out of core. And we would also like for the algorithms to process the data in as few passes as possible. Ideally, we prefer single pass algorithms. While 3D reconstruction is a very powerful tool, it of course has limitations. In the following, I will discuss some assumptions about the scene we have, which, when violated, will result in a poor reconstruction. Sorry, skipped one. Firstly, we assume that the scene is static. Nothing in the scene moves. More formally, the scene is subject to a rigid transformation. This is why it is so hard to capture people, animals, and also scenes with moving vegetation, for example. The workaround is to build camera rigs with synchronized shutters, effectively taking all the input images at the same time. Of course, this can be very costly. Next, we assume that the surfaces are Lambertian, that is perfectly diffuse. Any surfaces that don't have this property might be reconstructed poorly. This includes smooth plastics, metals, especially polished metals, and so on. The workaround is to use a diffuse scanning spray. This is cheap to do and can be made at home, but it alters the appearance of the model. Also, we assume that the object is densely covered in features. Again, any surfaces that don't have this property might be reconstructed poorly. This includes plastics, again, blank paper, or for example, uniform empty walls. The most common workaround is to employ 3D laser scanning. Ideally, in combination with color images. This is actually something that our software supports, but admittedly, it is a very costly solution due to the cost of the actual scanner. Another assumption is that the surfaces are opaque, that is, any transparent or translucent surfaces may fail to reconstruct. The workaround is again to use a scanning spray. Summing up, there are many limitations to photogrammetric 3D reconstruction, but the industry has always found a way to work around those limitations. Problem is that these workarounds are time intensive and labor intensive and cannot be applied in every situation. For example, 3D laser scanners have range limits, and you wouldn't spray a precious work of art. Additionally, recall that 3D reconstruction is being done at home and on a budget. These customers can use only some of these solutions. For example, the scanning spray or nose projection you can see in the picture. I argue that removing any of these limitations would make 3D reconstruction much cheaper and easier, especially for the non-expert users. This is going to be my best guess at the future evolution of 3D reconstruction. This is the current state of the capabilities. As you can see, 3D reconstruction at a high level is a decomposition problem. It decomposes the scene into its constituting parts, that being the camera poses and calibration, the shape and appearance, here in the form of radiance. To simplify the problem, we have some assumptions about the scene. The first step is not much of a prediction because some softwares already have an initial implementation of this. I expect 3D reconstruction to further decompose radiance into reflectance and illumination. There is a clear distinction between radiance and reflectance. Excitant radiance, which we have been capturing so far, describes the energy that is leaving the surface. Reflectance, on the other hand, describes the ability of the surface to reflect incident energy. This means that reflectance is an intrinsic property of the material, while radiance depends on illumination and on the properties of the material. Assuming a Lambertian reflectance model, both radiance and reflectance can be parameterized by 3 parameters. 1 parameter per color channel. This is why we are used to seeing both radiance and reflectance represented as a color texture map. While these two maps are visually similar, there's a key difference in that radiance contains lighting effects, shadows, and also a bit of highlights. This is why the process of computing reflectance based on measurements of radiance is called delighting, because these lighting effects are effectively removed. The main use of delighting is relighting by arbitrary illumination, I must add. This we can use to insert objects that have been captured into virtual environments plausibly. It is a common mistake to use a radiance map as if it were a reflectance map. As you can see, the result appears dark. This is because the radiance map contains extra lighting effects, predominantly the shadows. This is why I expect 3D reconstruction to capture reflectance, to aid the generation of assets and make them usable out of the box for relighting. Another step that I expect 3D reconstruction to do is to upgrade the reflectance model from Lambertian to a physically based one. The motivation is that the customers want to use the generated assets for photorealistic rendering. There are many ways to parameterize reflectance in a physically based manner. The most popular seems to be the Disney principled reflectance. On the left, you can see a simplified variant of this principled reflectance with 5 parameters. These parameters are the 3-channel base color, roughness, and metallic, which for most materials is just a binary decision between 0 and 1. This is what I expect 3D reconstruction to capture, to generate assets for photorealistic rendering, again, out of the box. Next, I expect 3D reconstruction to tackle some of the challenging surfaces that it could not reconstruct before. I think the motivation is clear here. We're tackling directly the limitations of photogrammetry. Finally, I expect an additional pre-processing step of the images to be introduced, a color correction step. To see why this is necessary, we have to consider that most of the input images provided by users are captured with consumer-grade hardware, which has a lot of automatic assistance mechanisms. These include optical enhancement, such as focus, but also linear color enhancement, that being exposure, sensitivity, and white balance. Unfortunately, there are also non-linear color enhancements, which we call photo finishing. Photo finishing are non-linear color enhancements designed by the manufacturer of the device to enhance the image, which is expected to become an 8-bit sRGB JPEG image. The actual implementation is proprietary and it varies. The actual behavior that is varies based on the manufacturer, on the camera being used, on the selected capture mode, and even the actual content of the image. For example, does it contain people or not? Or what's the lighting like? There are no metadata with the JPEG image that we can use to decide what kind of photo finishing has been performed. And this is a problem. Luckily, there are many problems where this color nonlinearity can be successfully ignored. We ourselves have been capturing gradients without regard for this. After all, whatever makes the input images look as good as possible makes our output textures look good as well. We were content. Unfortunately, there are many methods that depend on color linearity. For example, white balancing or rebalancing after capture, HDR reconstruction, and I would argue that high quality lighting estimation and material estimation depends on color linearity as well. And since 3D reconstruction aspires to do lighting and material estimation, I believe that 3D reconstruction has to reconstruct or restore color linearity as well. So this is my complete vision of a possible future 3D reconstruction. We can see that the decomposition problem has been extended and all the assumptions about the scene have been relaxed, with the exception of the static scene assumption, which I expect to stay. Now, let's have a look at some research problems that might help us tackle these future challenges. Firstly, radiometric calibration is a classic problem and is exactly what we need to undo photo finishing and restore color linearity. Technically, we are estimating the camera response function, which maps the pixel irradiance to pixel values. We limit ourselves to single image methods because the existing multiple image methods require varying exposure, which we cannot provide. Interesting problems include grayscale image calibration, which has been achieved before, but not at the quality of color image calibration. Also, we're interested in any methods that have varying camera response function for each of the channels. As it stands, all the single image radiometric calibration methods assume that all the color channels share the same camera response function. Lighting estimation is another interesting problem. It has become popular lately due to its applications in mobile AR, namely real-time object insertion and relighting. Thanks to that, we now have performant methods that operate on a single image. Interesting problems include, we would like to see more methods that are general, not specific to indoor and outdoor scenes. This is understandable since indoor and outdoor scenes have wildly different characteristics of light. We would also like to use the data that we have available in 3D reconstruction. That is, we have multiple views and we know the shape. Predictably, neural fields are also of interest. These approaches, primarily based on nerve, have been shown to surpass photogrammetry in appearance acquisition of challenging surfaces, such as featureless, highly specular, and partially transparent surfaces, as well as volumes and hair. This is interesting to us because it directly tackles our limitations. Open problems are many, but what's interesting for us is mesh generation. This is because the industry will continue to use the mesh as the surface representation for years to come. And we need a good mesh generation method to satisfy that. Reflectance estimation is also something we are interested in. Specifically, we are interested in physically based parametrization, ideally the 5-parametric principled reflectance that I have introduced. There are many possible approaches to this, including running neural networks on each of the input images, doing differentiable rendering to optimize a classical scene representation. Also, there are nerve-based methods that directly estimate these 5 parameters, such as the one I have figured for here on the right. What we see as the main problem is comparing these methods, because there is a distinct lack of data sets. You see, what we need is data sets annotated with reflectance. There are synthetic data sets that provide this. Pictured on the right is a synthetic dataset generator called Open Rooms. Efficiently capturing at a large scale real-world datasets is, however, problematic. This is because precisely capturing reflectance is an involved, time-consuming process that requires specialized equipment. To amuse you, I have prepared some examples. On the left, you can see a goniomphotometer that captures precise reflectance at a point in a laboratory environment. On the right, you can see a portable device called a light drum that can be positioned onto walls and floors, for example, to capture reflectance texture in a small patch. Another interesting topic is object completion. We have the problem that reconstructed models often lack details in small areas that were visible by just one camera, or perhaps none at all, completely unseen surfaces. Needless to say, these aren't reconstructed too well. So what we need to do is to hallucinate the missing parts and complete the object. One of the final topics is texture post-processing. We would like to apply image space methods, which are mature. There's a large body of work and they are successful at what they do. We would also like to avoid processing each of the input images separately, augmenting them, then trying to merge the result into a texture. In contrast, we would like to process just the texture, just once. This would open many applications, such as sharpening, upscaling, and in-painting the texture. There are two main interesting problems from our viewpoint. Firstly, is efficiently generating local patches around a texel. Seams in the texture, of course, have to be considered. So this leads to some efficient local parametrizations. Secondly, it remains to be seen if there is a way to apply global methods, that is, methods that require access to the entire image. You see, there is no straightforward way to have an entire image when it comes to textures. Last but not least, I would also like to stress that we have always been and always will be interested in one of the core problems of 3D reconstruction, which is image matching. Specifically, we are interested in wide baseline matching, any advancements in matching of unordered image sets, and matching that is scalable to tens of thousands, even hundreds of thousands of images. With that, let me conclude. We have seen that 3D reconstruction is generally applicable and scalable, but has many limitations. Firstly, it cannot handle challenging surfaces, such as featureless, specular, or transparent surfaces. Secondly, it cannot produce assets for photorealistic rendering out of the box. To overcome these limitations, we have a variety of open problems that must be tackled. For anyone interested in jobs at Capturing Reality, please contact the email that is on the screen. And with that, thank you for having me and thank you for your attention.
Thank you. We have one question from Zoom. So it's from Henry Kang. And he says that he likes reality capture. However, he wants to know if there is any plan for improvement on poor images, because the problems in structure from motion is that it always requires high resolution images.
Poor images, I see. Well, I promised I wouldn't comment about the specifics of the methods, but yes, poor images are always an issue. But our standpoint is mostly that the customers take a lot of images, and rather than fixing the poor images, our approach will always rather be to remove the poor viewpoints rather than fix them and include them. Hopefully that answered the question.
I have a similar question, but like, can you comment between having like a little number of high resolution image versus like video, which have like a lot of images, but like lower resolution, maybe blurred and so on?
Yes. So what are the advantages of having many low resolution images against having few high resolution images? From my experience, having high resolution images, although not that numerous, is advantageous. This is because we can use a stereo pair of a high resolution image to create much more detailed shape.
Thank you. I have one question myself, which is I'm in industry now, where I come from academia, and I'm still, very close with all of these new papers that come out all the time. And I would like to know how do you approach this? Do you actually like look at papers that come out? You try them? Do you adopt them? Maybe.
So you're interested in the actual process of applying science at our company. Yes, we study papers and we try to apply them ourselves. But as I mentioned, we are a really small company. There's about 12 active engineers. And with our large-scale application being used by this many users, we have our hands quite short. So actually, there's very few time to try a method. That unfortunately means that when we go and venture to try a method, that we have to be doubly sure that it's going to work in advance. There is very little room for experimentation.
Thank you for that talk. Can we send the speaker? So we'll have a coffee break now. Can you go back to the slide? Just so that we have the numbers on the board, the other ones. So we are actually under time. Let me put this quite nice.
Videos and slides.
So please come back by 3 if you would like to attend the second session. And now we'll have a poster session. Can you open the slides? No, not the slides, the Google slides. Our Google slides. Our Google slides, just so that they have the numbers.
Yes. So, I didn't
We present that
understand
over
your
Zoom.
question.
Sorry. Safari, beautiful person.
Why?
It's okay, just making fun of it.
So you mean this?
That's this. Actually go to down to the coffee thing. I just wanted to open this before. No, it doesn't. It is not. It's this one. Before this one. Okay. We can maximize it. Okay, that's what the CVPR told us. I don't know. We can go and check it out now. They should be there. I thought. I mean, I saw the numbers. I think. I'll go.
Is it okay if I move my laptop here side by side?
Yeah, that's fine. It's perfectly fine. Oh,
I mean, I'm the first one, so I.
yeah.
Let's come here and check after uses of this.
Did you send?
I just, you guys sent, I think you downloaded them. Maybe. I
Yes.
just want to check that they are.
Slides.
Should we mute? So.
But one mention, I mean,
Resume recording. There is sound. Cool. But actually, we don't have a whole. Oh, wait. Okay, but if we start, we can start.
So we can start with this one, and hopefully Daniel will show up.
Okay, so your mouse. Okay, we resume our workshop with paper presentation, and like please skip questions like to the end and the talk. And so here is first speaker from Amazon. So yeah, that's.
Just a second. What are you looking for? The cursor.
What?
I wanted to make this like smaller. But
What do you mean smaller?
I mean, slide this separator.
I have no idea
Oh,
how
it's
to
okay,
do
it's
this.
okay. No, it's okay. Okay, so hello everyone. My name is Alin Popa, and today I'll be presenting you our work entitled Unstructured Object Matching using Co-Salient Region Segmentation. This is joint work with my colleagues Ioana Sabina Stoian, Ionut Cătălin Sandu, and Daniel Voinea. We are tackling a new problem, that of unstructured object matching. This initially derived from a compliance-related use case. So part of the automated product check pipeline is to ensure whether a product or an object depicted inside the catalog matches the product from the regulatory documents describing it. So visualization of this process can be observed here. We are dealing with an inflatable pillow. And it is visible that on the catalog side, we are dealing with advertising related content where the background is emphasized or different interacting objects with our object of interest, such is the case for the pool and the children. So the focus doesn't drop on the main object. And on the document side, we have safety and regulatory aspects of the object, which are emphasized. However, the most difficult aspect that we encountered and why we designed this method is that there is no geometrical structure to rely upon in order to apply algorithms or matching algorithms which are based on structural key point correspondences. Here are a couple of image pairs illustrating our targeted use case and emphasizing the difficulty of the proposed task. In our case, we mostly dealt with objects which were designed for children, such as toys, clothing, Lego sets. And for example, you can see in the right upper corner, costume, which in one image is dressed, children is dressed with it, and the other is neatly folded on a table. For this purpose, we collected our own data set, which we entitled Toys in Context, TIC data set. And basically, we selected products from the catalog, which fall under the toys category. We downloaded all the corresponding images for each product. And in total, we had like roughly 2,600 unique objects. Here are a sample of objects, a teddy bear and the Lego set, and their corresponding images. And during the labeling process, we asked the labeler to assign a match or non-match to each image pair. And if there is a matching region, to draw a segmentation mask around both from each image. So in total, we ended up with roughly 13,000 images, pairs of images, with a 50-50 ratio between the two. Here are illustrations of pairs of matching objects from TIC dataset, and each pair is highlighted using a green bounding box. And I also wanted to emphasize the difficulty of the task and the lack of structure between both images. So in the following, I will provide like a high overview regarding our proposed framework and the involved components, followed by an in-depth technical analysis with intuition of why we did certain choices. So the way we approached this task was for input pair of images IA and IB to first compute a correlated image embedding representation. Next, we retrieve these similar regions from both images via segmentation task through MA and MB, which either depict the same semantic class or regions with the same appearance. Lastly, we use a binary classifier to decide if there indeed exists a match or not between the two. So as fundamental computational blocks for our framework, we have the coder and the matcher, which are our contribution to this work, and I will emphasize them in the following. So the coder component was inspired from the encoding part of the UNet segmentation framework introduced in 2015. We use basically successive computational blocks denoted with psi with a separate branch for each image. The difference with respect to the original UNet architecture is that at each downsampling step, we merge the resulted signal. So the entire intuition behind this decision was to constrain the semantically similar regions of both images to have the same feature representation by leveraging this mixed signal strategy. Having feature maps, resulting feature maps FA and FB from the previous step, the coder, we combine them together to obtain cosalient region segmentation of both images. And this is achieved via two segmentation heads, sigma A, sigma B, which produce two segmentation masks and are penalized by a cross entropy segmentation loss. And having these masks, MA and MB, we retrieve the foreground regions, foreground region embeddings RA and RB. Lastly, we have the final component, the matcher, and it receives as input the previously masked foreground region embeddings RA and RB. This might have different dimensionality according to the segmented objects. And the main concept is to construct a tensor with all the possible pairings between RA and RB, which is then weighted by the similarity matrix S between the two. For S as a metric, as a similarity matrix, we use the cosine similarity, proving superior results over the L1 and L2 metrics. And finally, using a classifier head phi, we obtain the final matching decision for the inputted image pair IA and IB. So as evaluation metric, we report the precision recall and F1 for the matching class of objects. Given the fact that the problem introduced was novel, I mean, it is a novel problem, we couldn't find any directly suitable methods to apply to our use case. Thus, we considered applying two flagship methods for image matching, like orb and superglue, introduced as CVPR 2020 and presented earlier. Both methods rely on structural key point correspondences across pairs of images. Thus, we do not expect them to perform at high standards. And as a result, we have an F1 score performance of 67 and 68% respectively. And additionally, we performed several ablation studies demonstrating the impact and usefulness of the design choices we made with coder and matcher, in the sense that as an alternative for coder, we use a Siamese ResNet 50 architecture. And for matcher, instead of using this whole heuristic with feature pairing, we use a simple pooling operator first over the entire image embedding, FA and FB, and then over the cosalient region embeddings. As you can see, the worst performing method involves the embedding over the entire image with a 46% F1 score. And we associated this to the fact that the background encoded a lot of noise. And the best performing one is Scott with matcher. However, the ResNet 50 Siamese backbone also performs like on similar terms. Here are a couple of matching results and their corresponding segmentations. So we have grouped them by 3 columns, and on each column we have, like on the first row, the input image, the original RGB, the segmented masks. And I want to emphasize a failure case here in the left upper corner. We have a matching between 2 costumes, and additionally, the segmentation highlights a costume with similar appearance. And this usually might to induce confusion during the matching process. To conclude, we have presented a novel niched matching use case of objects with unstructured geometry. We proposed a baseline in the form of a matching framework leveraging cosalient region segmentation. And lastly, we provide competitive results over other strong baselines using key point-based feature correspondence. Thank you.
Do we have any questions for the speaker? Okay. Then I just had one, which is, so you tried local features as a baseline.
Yes.
To me, like a classification algorithm of some sort would seem a more like logical baseline. Did you try that and did it do worse than this?
Yeah, we tried that and it did worse than this. I mean, we tried a lot of other experiments, but just we synthesized the ones with the most relevant score.
Okay, I think it'd
Yeah.
actually be interesting to have that baseline, but
Yeah,
as long
yeah,
as you
yeah.
tell me that it's kind of worse than that, I think, because if you read the paper, that's kind of like what shouts at you, right? But thank you. Let's move on to the second speaker. Daniel, are you around? You can do it here.
Yeah.
Perfect. So the next speaker is Daniel Ledon, who you should know about since Tom talked a lot about their joint work. He's now at Meta, and the talk is about NeRFLs, renderable neural codes for improved camera pose estimation.
Great. Thanks for the introduction. As Ed said, I'm Daniel Ledon, and I'll be presenting some work I did with collaborators over the last year or so. This work was led primarily by Gil Avraham, who did an internship with us. And yeah, cool. So let me just move this. So thinking about image matching and localization, to me, there are two key styles of image matching and localization that come to mind. The first is indirect and sparse. So the key strategy here is we extract primitives from images, we match them, and we use some sort of reprojection error to drive a pose optimization process. Actually, let me X this out. And you've probably heard of lots of methods discussed today: SIFT, D2Net, superglue. This is also the core mechanism that's used in systems like ColeMap, OrbSlam, et cetera. And one really nice thing about this style of optimization is the ability to do wide baseline pose estimation. Basically, as long as you can extract points and match them across wide viewpoints, then you can use this to drive a lot of really challenging image matching problems. This is additionally really nice because it has a lightweight memory footprint. If you want to, for example, scale this up to map an entire city, it's pretty clear on how you could do something like that. One limitation with these types of methods is that they rely quite heavily on having precise sub-pixel repeatable detection. Basically, any errors you have in detection are going to be seen later in the pipeline in your pose estimation system. And so you oftentimes have to make this really hard decision up front. That's a discriminative decision, and you're more or less stuck with it later on. There's another class of techniques that rely more on dense alignment. So using all the pixels to drive the pose estimation problem, typically using a Lucas Canade style alignment. Works like DTAM, Pixlock, IMAP, lots and lots of works have this fundamental alignment at its core. This is nice because it uses a lot more image information, which means that you can get a lot of subpixel precision. One limitation of this is that oftentimes you'll require a dense map representation, which might be prohibitive for AR and robotics applications. Additionally, they require a good initial pose. So one of the thoughts we had in going about this research is, how can we get more out of points? And some of our work was inspired by surfels. So for those of you that don't know, surfels is a rendering primitive used in graphics over the last 20 years that essentially treats each geometric primitive as a disk. So you define a 3D point in space and you have a disk that's typically tangent to some surface. And so our idea was, well, can we treat points as being locally dense? And in the end, set up a joint sparse and dense optimization. And I'll tell you a little bit more about what that means. So, going about this, we thought, well, we could use these disks and we could approximate the scene with planar patches, but can we go beyond disks? And so a lot of our work was inspired by a lot of the new work happening with NeRF and neural radiance fields, which do a great job of being able to render 3D points and 3D scenes from 360 degrees. So one of the nice things about this framework is that it allows us to render patches around each point that for non-planar scenes, because we know that points are detected and fire on a variety of different types of scenes, not just planar scenes. And we thought, well, maybe we can have, instead of a single nerf represent the entire scene, have a single nerf that is code conditioned. So there, so in addition to having a 3D, hold on, that's a bit of a, should I mute it or no? Yeah, if you could mute in the background, that'd be great. And so yeah, that was kind of the thinking behind this work. So let me see if this video works, hopefully. Yes. Cool. So here's a visualization of them. So what you're going to see, and I'm going to freeze the frame just for a second so I can explain it. Let's see. So on the left-hand side, you see the RGB image. And well, I can't really, when I pause it, it turns black, but I'll just repeat it. So on the left-hand side, we see an RGB image. We see, these are super points. We run a super point detector and we filter them quite a bit. So we have only maybe 10 or 20, maybe 30 detected per image. And for each point, we attach this neural renderable code. And so what you see in the middle column are just those codes being re-rendered back into the image. And on the right-hand side, we overlay the nerfles being rendered back onto the original image. The idea is that on the right, you shouldn't really be able to see a difference between what's being rendered at the patchwise level by the neural radiance fields and what's being seen on the image. And so the key idea is, well, if around each point you can attach this neural radiance field, we can optimize jointly the geometric error, which is the reprojection error, and a local photometric error. And so that's where nerfles comes in. So in nerfles, we represent the scene not only with a point, but we attach a code to each point, as well as a pose. In this case, the pose is pretty simple. It's just a 3DOF orientation. And the code is a 64-dimensional vector that's input into a nerf model. So the task that we use to evaluate the nerfles is 2-view pose estimation. So in this case, we have a query, a reference image, and we want to estimate the relative pose between the two images. So how does localization with this code condition nerf work? So in order to do localization, we solve a joint optimization problem. So you see the blue array pictured, that's our high dimensional code. We have this neural radiance field, and this neural radiance field will basically get us what you see, this rendered 3D map primitive. So we have a local appearance of that point. And since we know the assignment from a matching stage, let's say we used superpoint detector or descriptor or your favorite matcher, then we can basically first run the geometric optimization and then refine it and get it really precise using this local photometric error. And on the left is just kind of for fun, but we are interpolating through the through this high dimensional nerfle code space. In this particular model that we trained, the images were a bit dark, so it comes out to looking like this black coal, kind of a little bit of a mess, but I think it still looks really cool just to see it interpolate through these different shapes and appearances. And so, so going to a little bit of more detail on how this pose estimation system works is step one, extract key points and descriptors, match them. So you see the red lines, it's like standard sparse map style optimization. Step two is we optimize for the codes of the nerfle. So we just set up an optimization problem where we refine that code. Just basically to render a low photometric error in our query and reference frame. And then lastly, we combine these two errors. Again, we have the reprojection error and the photometric error into a joint estimation problem where we're optimizing over the camera pose, and we refine the nerfle code a little bit too. And looking at results, so we evaluated this on ScanNet, where we selected essentially pairs of images with overlap. And we show that you can add this idea of NeRFLs to a variety of input features. So we tested SIFT D2Net SuperPoint. So you'll see the bolder numbers indicate that we get a little bit of a boost in performance. You'll note that this approach that gets the biggest boost in performance is SuperPoint, because in SuperPoint, there really isn't a lot of subpixel localization. There are ways you can do it, but the vanilla SuperPoint doesn't have that. So you really see this NeRFLs method shine for key points that struggle a little bit with key point localization. And we also compared it to having just a dense representation of the scene with iNerf, which if you just try to train that vanilla, it basically fails because the scenes can be too big. Because iNerf a lot of times was designed for object scanning style data sets rather than indoor rooms and scenes. And then the last baseline is what happens if we just use a surfhole, basically a planar approximation of the surface, rather than having the neural radiance field, which can be more flexible. So yeah, this is a fun project. I think a couple limitations, scalability. So each model has one NeRF per scene. So I think as of now, from when we started this work to now, there's been a lot of explosion of work around NeRF. So I think there's lots of awesome ideas on how we could improve scalability. Rendering speed, this takes about a minute or more to estimate the camera pose, so it's quite slow. But there's lots of work now in speeding up NeRF. And lastly, in terms of the optimizer, we used a simple first order optimizer, but second order one like Leavenworth-Marquardt should be a lot faster. And that's essentially it. So in summary, NeRFLs is a way to augment 3D points using a 64-dimensional rendering code and pose. This can be added to any existing local feature. And in the end, what we're left with is a locally dense, but globally sparse 3D map representation. Thank you.
Does anyone have a question for Daniel?
I'm wondering why they say resolution behind this method was better than the smart method. Is it just because you need more pixels, negative more information?
Yeah, you basically cut to the core of why this is important. I think, like I said at the beginning, if you have errors in your detector that mean the point is just not really quite where it needs to be, then this local optimization has more information coming into the optimization problem, and it can kind of adjust and fix those little problems that can happen in detection. So
it's like reaching the better accuracy and so we can get.
yeah, so SIFT, for example, does have subpixel localization and it works quite well. But one of the things you'll notice is as you go up in the semantic space of what you're detecting, it becomes harder and harder to put a very precise point. Like, for example, a chair detector. Like you ask a human to pick one point that represents the chair has subpixel repeatability from all views. It's really, really hard. So I think as we want to incorporate more and more semantics into our 3D representation, having this photometric style optimization is one way to account for errors that might have happened in that process.
Yes, we'll move to the next talk. So the next talk is also from Meta. It's Picture Carry Networks by Hugo Chapman from Paul Lupon. Did you finish already?
Yeah,
the PhD? So now it's time to Chapman.
Go on. Used to be a okay. Yeah. Hello, everyone. So yeah, very excited to be presenting the work I did in a previous internship at Meta Reality Labs. So this work was done in the supervision of Vasilios Mantas, and it's called Feature Carry Networks, neural surface description for camera pose refinement. So the motivation for this paper was that stemmed from the observation that having truly viewpoint invariant feature descriptors is quite tricky. Like it's very hard to obtain descriptors that will remain completely invariant to common perturbations that you can encounter in natural images when you have different camera poses. So one example is like maybe this bottom row here, where you have strong out of plane rotations. It's very common that learned descriptors and also more traditional handcrafted descriptors will have trouble remaining invariant. And so this is on the right column. You can see, for instance, a correlation map that were obtained by extracting first sparse descriptor, so a descriptor at the point in red on the reference image, which you can imagine is the reprojection of a 3D point, and computing a feature correlation map with the dense representation from the query image on the right. And the same goes for the upper row, where we have occlusion, which is even more challenging and is something that was commonly encountered in many computer vision applications. So instead of trying to achieve true viewpoint invariance, like the idea of this paper basically was to try and instead model the variance, basically the view-dependent effects directly in descriptor space. So to do that, we introduce feature query networks, or FQNs for short. So FQNs are basically array-based MLPs that are trained to model the view-dependent effects that you will obtain in arbitrary feature descriptors, basically. So this is basically a simple model that will take as input known geometry from 3D geometry from a given scene, a camera pose as well, and will be trained to output high dimensional descriptors. So in our experiments, descriptors range from like 128 to 512 channels. So if you compare that to a model like NERF, for instance, it's a bit easier because we only we assume the geometry is known, so we only query the model at known 3D coordinate locations and don't try to estimate the density. But on the other hand, we have a much harder task, which is to regress really high dimensional descriptors, which are quite complex. So the way we parameterize this model is as follows. The FQN will take as input a 3D point, so 3D point coordinate that will maybe come from 3D data from like SFM model, or a depth sensor if you're an indoor scenario, for instance, as well as the viewing direction that encodes sort of the pose of the camera. The ray length helps modeling the changes in scale and the proximity of your camera with certain objects. And then we have some the camera roll and the focal length to encode some of the more planar transformations that can lead to perturbations in descriptors. So if we take this model and train it with, in that case, D2Net as supervision on a given scene, so then we can basically overfit it. And at test time, so assuming that we know the pose of the query image, we can regress the descriptors from that novel viewpoint. So basically what we do is sort of a novel view synthesis directly in descriptor space. And what this does is that it enables us to basically hallucinate descriptors from these novel camera viewpoints and bridge this viewpoint discrepancy gap that we have between the reference image and the query image. And that leads to much better results, as you can see. So we derive two applications from the FQN for camera pose estimation. The first one is FQN-based direct alignment. So if you look at the traditional featuremetric minimization formulation, basically you try to minimize the distance between a descriptor that is assigned to your 3D point and a dense feature map that is computed from your query image that you want to relocalize and estimate the camera pose for. And the problem is that this 3D descriptor, again, maybe has been computed from a reference image that had a camera pose that was really very different from your query image. And so you have this viewpoint discrepancy that can perturb this minimization procedure. So now that we have the FQN, we can reformulate this minimization problem. And instead of having a fixed 3D descriptor, we can dynamically query it to update itself basically based on the current estimate of the camera pose. And that helps avoiding getting stuck in some of the local minimum. So we have a number of quantitative experiments in our paper where we show basically that this helps slightly improve the performance of certain descriptors, and more importantly, that if we take a very simple descriptor that, so in our case, we take a MobileNet v2 backbone and train it with a simple contrastive loss, we see that we are able to achieve performance that is on par with some of the most advanced relocalization methods like PXLOC, for instance, just by the fact that we have learned to model how this descriptor changes with respect to camera poses using FQNs. A second application that we derived is what we call this iterative PNP plus Transac. So the idea here is that if you follow a traditional structure-based relocalization algorithm, you can basically learn, so you can basically first compute 2D to 3D key point matches, feed that to a PNP plus Transac algorithm, and have an initial camera pose estimate. But now that we have an FQN that is trained on a given scene, we can close this loop and take that camera pose estimate that we have to basically re-update the 3D descriptors at this estimated camera pose, recompute the 2D to 3D correspondences, and solve for the camera pose again. And so we can iterate like this a couple of times, and we show that this helps again bridge some of the viewpoint discrepancies that we have and improve the camera pose estimates in the end. So this is a visual, so qualitative visualization of this. So basically on the top, you have the reference image with the projection of the 3D points in red. On the right is the query image with the estimated correspondences. Sorry, the reprojection of the points at the estimated camera pose. And you can see that after a couple of iterations, we managed to improve the camera pose by updating the 3D descriptors and recomputing the key point matches and solving for the PNP plus Transac. Yeah, so that's basically it. So we, in this presentation, just introduced this concept of the feature query networks that can be used in two computer vision, camera pose estimation applications. It's still limited in a number of different ways. It's a scene-specific model that is trained on a given descriptor, so there's probably a lot of room for improvement from there. But we believe this is an interesting way of bridging a viewpoint discrepancy gap, and could also be a train to model other types of perturbation descriptors other than viewpoint, such as illumination or whatnot. Yeah, that's it. Thank you very much.
Questions? Okay, I have a question actually. So how is it like dependent on the viewpoint distribution in the training set, or you like synthesize new, or like how it would work if you have like quite limited thing?
Yeah, that's a good question. So I think it's definitely helps to have more camera poses because hallucinating, so regressing a descriptor from a completely novel viewpoint that is sort of out of the distribution would most likely not work. I think it's a bit. I think there needs to be a lot more experiments because right now, even on the size of the descriptors or other types of parameters, that I didn't have time to do during this internship. But yeah, I think it definitely helps to have more denser sampling of the reference images to model things like the occlusion that I showed.
Thank you. Any more questions?
The next speaker is not here, and I think we'll just play a video that he sent us. It's a minute. So the next talk, which is pre-recorded, is learning cross-segmentation by segment swapping for retrieval and discovery by Shishan and co-authors. Shishan is a PhD student at Colgupon. No, that's coming from the. 1 second. The audio is coming through the projector.
But it should come out of this.
You would change something.
No, I haven't.
It comes through the speakers.
Yes, speakers. Speakers.
the mic to the speakers.
Yeah, you have to try.
In the code segmentation problem, which aims at finding repeated visual details in a pair of images. The problem can be formulated to have a binary mask prediction for each single image, where unmasked regions are repeated patterns. One example of a pair of images is shown in this slide. We use the transparency to highlight repeated patterns. As we want to learn a model to give us such prediction, the main challenge to solve this task is that there is no training data available to train the model. In this work, we propose a solution including training data generation and architectures to address the problem. Here is the plan of this talk. I will start with our key idea, code segmentation by segment swapping. Then I will show that our approach can be applied to image retrieval tasks. In the third section, I will show that our approach can be used to conduct discovery and code segmentation on a collection of images. Finally, I will conclude and give a brief summary to our work. Okay, let me first present our approach. Our key idea is to generate synthetic training pairs with duplicated patterns, which allows learning code segmentation. Precisely, we take annotated segments from Coco and randomly sample a background image. If we directly copy-paste the selected segments, the generated image has obvious artifact. Network can easily support segments through some simple clues, such as the gradient of the boundary, while this information cannot be generalized well on real testing cases. To alleviate the artifact, we propose to leverage Poisson blending and style transfer on the generated image, which leads to pairs that are more natural on the boundary and potentially harder for the network. Finally, our blending will generate a pair of images containing repeated segments. As a result, we also have access to the mask annotations and the correspondences of the segments. Here are some generated pairs. We show the source image, blended image, and both images with style transfer in the slides. We choose to blend one or two objects such that we are able to learn more complicated displacement field. Instead of using segments annotated in Coco, we also explore advanced unsupervised segments. For unsupervised segments, more details can be found in the paper. To learn code segmentation, we extract CNN features from the input images and conduct experiments using two different architectures: cross-image transformer and sparse and CNET. For both architectures, the input is a pair of images, and the output contains mask predictions and correspondences mapped for each image. For cross-image transformer, we have two modules: self-attention and cross-attention. Self-attention is the standard attention mechanism and compute attention only in one image with considering position encoding, where cross-attention compute attention in a pair of images without using position encoding. Sparse and CNET compute correlations between two feature maps. These correlations are resized to 40 tensors that can be processed with 40 convolutions. For both architectures, we supervise the training with the mask and correspondences annotations. The objective function is shown in the slides and contains three terms. Here, M and C correspond to the mask and correspondences respectively. The first term is the cross-entropy loss between the predicted and grand truth mask. The last term corresponds to the L1 loss of the correspondences on the repeated regions. In the middle, we add a loss to connect the mask prediction and correspondences prediction, which is the cross-entropy loss on the transported mask wrapped using the predicted correspondences. The output of the network can be used to perform retrieval tasks. We evaluate the performance on Bruegel for one-shot detection. The goal is to identify the same visual details in a database as in a query. We define a score between a pair of images. The score contains joint mask term and feature similarity term. The joint mask term is the product between the transported mask and the predicted mask on the source image. The feature similarity term corresponds to the cosine similarity between a pair of features defined by the predicted correspondences. Here are some visual results. We show the predicted masks as a transparency. We can see in the first row, even there are multiple objects repeated, our approach managed to spot repeated segments. In the second row, the repeated cards are in different contexts and in small scales. Our approach can still give reasonable prediction. Quantitatively, we report performance for both retrieval and detection. For detection, we obtain bounding box by first cropping a big patch around the predicted correspondences, then computing cosine similarity on sliding window proposals. We employ features trained with MoCo, a CNN feature extractor. For retrieval, both the cross-image transformer and sparse and CNET outperform previous approaches by an important margin. For detection, we find that the predicted correspondences of transformer are more precise and leads to superior performance compared to previous approaches. Note that previous approach leverages multi-scale feature matching and ransack, which is more complicated. Our approach is simpler and better. We also conduct experiments using unsupervised segments, which achieves comparable performance. These results suggest that our approach is not relied on the COCO annotations. Our approach can also be used for place recognition. We conduct experiments on Pittsburgh and Tokyo datasets. The Pittsburgh dataset is a large-scale dataset with more than 10,000 database images and 8,000 queries. The Tokyo dataset is particularly challenging as the queries are taken in nighttime while the database images are in daytime. Here are some real results using our models trained on synthetic pairs, which demonstrate a good generalization on both datasets. Quantitatively, we also achieve comparable performance compared to state-of-the-art approaches. This result is especially impressive since these benchmarks are very competitive and many dedicated methods leverage geo-referenced images or real correspondences for supervision. On the contrary, our approach is generic and relies solely on our synthetic segment swapping training. Note that we also conducted detailed analysis on the architectures and losses, which can be found in our project page. Instead of focusing on identifying repeated segments from pairs, in this work, we also explore how to perform discovery on a collection of images. Our solution relies on the predicted masks and correspondences to build a graph and formulate the discovery as a clustering problem on the correspondences. Precisely, we build a graph where the nodes are correspondences. Here V is a set containing correspondences. We show the S nodes in the slides. The nodes can be properly defined with the indexes of the source and target image SI and TI. Predicted correspondences XSI and XTI. Finally, the mask prediction MI. The edges are consistency between the nodes. Precisely, we consider 3-cycle consistency. We only connect the correspondences which have exactly one image in common. Here are 2 nodes, which are 2 correspondences. Let's assume the correspondences I and J are both connected to image S. The formula is showing on the top, which seems to be complicated, but the concept is simple. We take into account both mask predictions and only connect the edges that the distance in the shared images are closed. We then consider the 3 cycles with XSJ, XTI, and XTJ. We transform XTJ to image TI using the predicted correspondences from TJ to TI. And we measure the distance between the transformed position and XTI. The same operation is for XTI. We transform XTI to image TJ using the predicted correspondences from TI to TJ. And we measure the distance between the transformed position and XTJ. Given the correspondences graph, we use the spectral decomposition of this adjacency matrix to obtain clusters of correspondences for discovery. Precisely, We first compute m principal eigenvectors, then perform k-means with k clusters. To reduce number of nodes in the graph, use mask predictions to remove the nodes and correspondences that are with low confidence. Some discovered clusters on Bruegel are visualized here. As we can see, the discovered patterns are not necessarily silent objects. They're also with diverse styles and different contexts. More results can be found in the project page. Apart from application or artworks, our approach also achieves competitive performance on object discovery benchmark, which again demonstrates the robustness of our approach. To summarize, in this work, we show that it's possible to learn code segmentation with only synthetic pairs. We show the model trained on synthetic pairs work well on retrieval tasks. We also introduce correspondences graph for discovery and achieve competitive performance on object discovery benchmarks. Note that our code, data, and more experimental results are available in our project page. Thanks for your attention.
Let's thank the speaker in spirit. Thank you. No questions since it's not around. The next talk is also going to be a pre-recorded video. It's the AAE, disparity alleviation autoencoder towards categorization of heritage images for aggrandized 3D reconstruction by Dikshit Hegde and other people. Okay.
Hello everyone, myself Dikshit Hegde. I'm glad to present our DAAE, that is disparity elevation autoencoder towards categorization of heritage images for aggrandized 3D reconstruction. This work is carried out with Tejas Anvekar, Ramesh Shuktavi, and Umamuddin Godi at Center of Excellence in Visual Intelligence, Kerala Technological University, Hubli, India. Due to natural calamities, there is degradation of heritage sites. There is need for the digitization of heritage sites. Through digitization, we can preserve the heritage sites for future generation. We can also further create a walkthrough of AR and VR. We can generate 3D models of heritage sites using single view or multi-view images, LiDAR, scanners. But scanners and LiDARs use pre-processing steps. Collection of images of heritage sites across the globe is time-consuming. Towards this, we perform the collection of images through crowd and name that the data has crowdsourced data. The data is unstructured and unlabeled, resulting in poor and merged 3D models as shown here. A minimal similarity between structures will create a merged 3D models. There is need for the categorization of these images, as there is no associative labels for the crowdsourced data. Unsupervised categorization, that is clustering, is one of the techniques. Categorization of high-dimensional data is computationally expensive and time-consuming. Clustering needs lower dimensional features, which is disentangled and have complete information from the image space. Dimensionality reduction methods like PCA, kernel-based PCA, etc. extract features from images which might not be suitable for categorization. Extracting relevant features with deep learning-based methods is current trend. For deep clustering, recent work uses autoencoder, which computes loss in image manifold space. Ali et al., that's DAC, in et al., that is IDC, computes loss in latent and image manifold space individually. But there is lack of information validation from image space to latent space. Towards this, we propose disparity elevation autoencoder, that is DAE. In DA autoencoder, we have a DA encoder where we tap intermediate representation of the data and the latent space. Towards optimization of the DA encoder, we model reconstruction loss consisting of MSC loss function and structural dissimilarity loss, where structural dissimilarity loss consists of 1 minus structural similarity of the input image and reconstructed image. We perform 3-point approximation for inducing a contractive and discriminative optimization through theory of indiscriminables. Towards this, let us consider a pair of images I, j projected in image space xi and xj. When propagated to DA encoder, we get intermediate space or neural representation space of the images AI and AJ respectively, and latent representation ZI and ZJ. 3-point approximation results in copying the constraints from image space to latent space. Towards this, we introduce Jacobian of neural representation and latent representation for inducing nonlinear independent component analysis. We estimate the distance between the pair of images in their respective space, and we minimize the distance using the model loss function as shown here. Here, the distance metric can be a MSC or MA function. We demonstrate the effect of proposed model on latent space representation. We can see that there is overlapping clusters in AE, but similar classes are disentangled in DAE latent space in both MNIST dataset and IDS10 dataset. We also compare clustering accuracy of our result of a proposed model with state-of-the-art method. In the MNIST dataset, there is an increase of 10% accuracy. For fashion MNIST dataset, there is approximately 4% increase. In USPSC dataset, there is approximately 5% increase. And for IDH, there is 18% increase than the state-of-the-art models. By applying IDC as a plugin to DA encoder, we compare the results with the model using clustering loss as an order. In fashion MNIST dataset, there is an increase in 9% accuracy from the SOTA method. We present the effect of DA encoder on heritage sites before and after categorization through 3D reconstruction. We presented DAE, that is disparity elevation autoencoder, towards categorization of images for better 3D reconstruction. A modified version of autoencoder which is robust and interpretable. It captures disentangled the features of images using disparity elevation loss function. Thank you. For more information, contact us at sevi@kdtech.ac.in.
Let's send speaker again.
So the last two talks are in person. Can the speaker come? Thank you. So the first one of the last two talks is detecting and suppressing marine snow for underwater visual SLAM, and the talk will be given by both Lars Martin Hodne and Arvid Leibel.
Thank you for the introduction. My name is Lars Martin Hodne. I'm joined by Arvid Leibel, and we're pleased to present a paper we made during our master's project on detecting and suppressing marine snow for underwater visual SLAM. So first of all, here's a video which shows you what marine snow is. Oh, I think I'll just switch to this version. Just a moment. Yeah, you can tell the white floating particles here is what we call marine snow. It's present throughout the open ocean at all depths, and it can be a bit of a headache for feature-based visual SLAM. And here you can see why. We've run the orb key point detector on this video sequence, and you can see it picks up on a lot of the marine snow in this scene. And we made a synthetic example and performed post-estimation on this, which highlights the effect of marine snow. You can see in the top point cloud, which is the sequence without marine snow, the yellow pipe here is tracked straight as it should. But on the bottom, when we introduce marine snow in the sequence, the tracking fails quite quickly, despite the use of staple SLAM methods such as ransack, ratio testing, and more. So this leads to our goal, which is to develop SLAM frontends which are immune to marine snow motion noise. And the approach presented in our paper was to use deep learning for key point classification after key point detection. We developed two schemes. First, a fully connected neural network, which classifies key point descriptors. And secondly, a convolutional neural network, which classifies key point image patches. Before we go into those, I will tell you about the custom data sets we made to train these and train and evaluate these networks.
Yeah, so there is not any ground truth available. So we create our own data sets. So we created a set of key points containing key point image patches or regions around each key point and the various key point descriptors. And then each key point is given a label of either clean or marine snow. The method we use to do this is to label trivial images, that is images that are either exclusively with or without snow. So on the top, we can see an image that is completely without snow. And on the bottom, we can see an image that is exclusively snow on a flat blue background. So this allows us to label on a per image basis instead of labeling each key point individually. However, this comes at the cost of quite low data diversity, as each snowy key point is now located on a flat blue background. So to increase our diversity in the data, we use superimposing. So here's an example of the superimposing we do. We start with the exclusively snowy image and extract the snow to create a snow mask, which we can then use to superimpose the first image on any random background of our own choosing. So here's the pipeline in a little bit more detail. On the left, we can see the input, which is the snowless background, and the snowy image, both of which can be sequences. And on the top right, we can see the output. So to do this, we use a weighted sum between the two images with the snow mask as the weight. And to generate the snow mask, we start by calculating the median color of the snowy image, and I'm calculating the pixel to median color distances for all the pixels in the image before we scale the distances by one of maximum distance. And then, because we only want the snowflakes and not the background to be included in our snow mask, we set a threshold where any distance below the threshold is set to 0. And to remove any shadows or dark areas in the image, we use a shadow threshold from the pixel values and set those to 0 as well. And then to reduce image artifacting, we do this last stage in a strided window with a 60 by 60 stride of 10 and average out over the windows. And then to extract the key points, we do key point extraction on the snowless sequence and extract the snow separately to maintain data balance. And then to make sure all the key points are still valid in the final sequence, we use filtering on the key points. The snowless key points are filtered based on their proximity to the snow in the extracted snow. And the snow key points are filtered based on the visibility in the final sequence by comparing the variance in the patch around the key point in the snowless sequence and in the superimposed snow sequence. And then to reduce the data, as we have quite a few lots of key points, we use random grid selection to reduce it. First setting out the key points, and importantly, computing the descriptors on the final superimposed sequence.
So to briefly cover the classifiers, the patch classifier, as I said, is a convolutional neural network. It's based on a multi-scale input where we extract patches at 3 scales and resize them to have the same height and width. The architecture itself is a rather standard CNN style architecture. So we end with a sigmoid output layer to give a pseudo probability of the inputs class. The descriptor classifier is a fully connected neural network. We found through testing that the OR descriptor was the best overall compared to Freak, SIFT, and VGG. And again, we have the sigmoid output layer to give the pseudo probability. And both of these networks are rather compact to keep inference speeds low. So summarizing the quantitative results on the test data sets, we found that models trained on unmodified data were, as predicted, unable to cope with the textured backgrounds from the superimposed data sets. When training on superimposed images, this did improve the performance on the texture backgrounds, back almost to the levels of the unmodified data. And also it did not worsen performance on that original unmodified test data set. We see that patch classification consistently performs better than descriptive classification, although this tendency was not as clear in the qualitative tests. And finally, given how good the performance is on these metrics, we think that improving the models further should not be a priority. Instead, focusing on the realism of the data set is what's needed to create results which generalize well onto real-world sequences. Because as we can tell from the qualitative results here, first from the patch classifier, in this case, blue indicates a clean classification, red indicates a marine snow. We can see that while most key points are classified correctly, there is some tendency to have false negatives where snow is classified as clean. Moving on to the descriptor classifier, this was one of the sequences where it outperformed the patch classifier. We can see particularly in the region in the upper left, the patch classifier struggled tremendously, and the descriptor classifier does a bit better, but still has some amount of false negatives. Going back to the point clouds from the introduction, we can see once we introduce snow classification, the bottom point cloud now matches the case without synthetic snow. This was the case for both key point classification schemes, and seems to indicate that as long as, or considering the differences in earlier testing, it seems that as long as we can reduce the number of unreliable key points below a certain threshold, that traditional key point prediction methods can do the rest. So to summarize, we presented two key point classification schemes to combat marine snow and SLAM. SLAM performance was similar between the two schemes, and we also found that snow can be extracted from textureless images and superimposed to improve data variety for our data sets. However, some work still remains to reliably classify snow on texture backgrounds to eliminate those final false negatives. Thank you.
As for the talk, do we have any questions in the room?
I have a question actually. So my question would be like, for like very core of approach, why do you you decided to remove key points and not denoise image first, like train some kind of model for denoising and then detect and clean?
Yeah, this was a common method, perhaps a few years back in image restoration works. But the issue is that these marine snow particles can be so large that denoising simply does not get rid of them all.
Mm-hmm. Oh, cool. Thank you.
We have one last paper talk. Speaker in the room. George.
It seems so.
So the last talk for this block is SE Laughter, which is a case for using rotation invariant features in state-of-the-art feature matchers. The talk will be given by George.
It depends on language, George.
I'll just say George, but then.
Hi, my name is George. I'll present this work, which is joint work with my supervisor, Fredrik. And here's the main takeaway straight away. So if you have a state-of-the-art image matcher like Lofter, you can modify the backbone by exchanging it from a CNN to a rotation equivariant CNN. And if you do that, you can obtain good performance on ordinary image pairs
as Lofter has, while improving performance a lot on rotated image pairs. All right, so what is Lofter? Many of you probably know. I'll do a quick overview. So there's a feature pyramid CNN that extracts some features at 2 levels. And the coarse features are concatenated with positional encodings and fed into a type of transformer. Then there's matching of these features and some refinement of the features using the fine level feature maps. Finally, we get matches from coarse locations in the first image to subpixel locations in the second image. So here's a failure case of Lofter on rotated images. You can see that it only finds matches on this very repetitive structure, and all of them are incorrect. And here's another failure on rotated images. Again, all matches found by Lofter are incorrect. And here are 4 more matches found by Lofter, and 2 of these are correct and 2 are incorrect. So can you tell which are correct? Here are the images. So actually the 2 left correspondences are correct. As you can see, they are just rotations of each other and some illumination changes. And the 2 rightmost correspondences are incorrect. So we would like the method to have more matches of the type to the left and fewer of the type to the right. So why doesn't Lofter give us more of the type to the left? Well, because the CNN backbone doesn't guarantee that rotated versions of patches actually have similar features. Now let's see if this GIF works on this computer. Seems like it doesn't. All right, I skip this. And the way to get a rotation equivariant CNN that I used was to go by this framework by Weiler and Cesa from NeurIPS 2019 called E2 equivariant steerable CNNs. And they have a very principled approach to constructing these rotation equivariant CNNs that builds on what's called representation theory in abstract algebra. And I won't have time to explain what that is, but they provide a very nice PyTorch package called E2 CNN, which makes it easy to construct these rotation equivariant CNNs. And I use that in my experiments. So let's have an example of a rotation invariant feature map or a feature field. So we say that a feature field given an input image I, a feature field F has rotation invariant features, or a more complex accurate name, if when we rotate the input image, the positions of the features also rotate, but the features themselves don't change. So for instance, a blurred version of the input image, if we have the input image on the left and then blur it and then rotate, we get the rightmost picture. And also if we first rotate and then blur, we get the rightmost picture. So that means that the blurred version of the input is a rotation invariant feature map. And more generally, we can have rotation equivariant feature maps. So for instance, the gradient field is such a thing. So that means that when rotating the input image, the features change position and they also rotate. I think this is commonly known as covariant features in the image matching community. I've used the word equivariant, and that means the same thing. And equivariant is the name that's used in these papers on rotation equivariant CNNs. That's why I use it. So here's the gradient field of this piano image. Again, if we rotate the input image, the gradient field will also rotate. Unfortunately, we can't quite see what happens here, but the arrows don't just move, the arrows also rotate, and that means that they are equivariant. And Weiler and Cesa in their paper give a very nice overview how to construct these equivariant layers that preserve this equivariance between very general kinds of feature fields acted on by the rotation group. So the idea in this paper is simply to take Lofter, replace the CNN backbone by a SE2 equivariant CNN. That means both rotations and translation equivariant. And for the feature maps in this backbone, we choose the regular representation of finite rotation groups And I won't have time to explain what that means either, unfortunately. But we use rotation equivariant features in the intermediate layers of this CNN and rotation invariant features in the output layers. So what's actually matched between the two images are rotation invariant features in this work. And here we see the image from before. We can see that SC2 Lofter managed to find matches that were unavailable to Lofter. And that's because the regions that SE2 Lofter finds these matches in look too dissimilar to Lofter because they are rotated versions of each other. Again, here's another image we saw before, and SE2 Lofter finds many correct matches. And here's the final example we saw where SE2 Lofter again outperforms Lofter. So in this work, we consider 3 versions of this SE2 Lofter, and they differ in what discretization of the rotation group is used. So either we use 4th rotations or 8th rotations. So these are quite coarse discretizations. And they also differ in the relative number of intermediate backbone features. So when we use these rotation equivariant CNNs, we get a lot more weight sharing than by just using ordinary CNNs. And that's why the number of learnable parameters drop when we introduce these rotation equivariant CNNs. And if we compensate for this by increasing the number of backbone features, we get more learnable parameters, but we also get a larger CNN and hence more compute time and memory consumption. So there's some trade-off there. And here's some quantitative results on homography estimation on H patches. And also on H patches R45, which is a version of H patches where I've just rotated the images 45 degrees arbitrarily. And the main takeaways from this is, I think that SE2 Lofter, the big version without the star here, it can outperform Lofter on H patches in general. And also on H patches R45, SE2 Lofter simply outperforms Lofter a lot, all versions. And also that the performance of SE2 Lofter in general improves more on the viewpoint sequences than on the illumination sequences in H patches. Okay, here's some future ideas. There is actually an issue in the positional encodings that they are not rotation invariant. So if you want the complete rotation invariant method, you should fix this. You can do this by using relative positional encodings or something like that in the transformer layers. We could try to incorporate equivariant or covariant features. This was also, I learned a lot about this yesterday in the affine correspondences workshop, which was nice. And also we could try incorporating scale equivariance somehow. And we could try to find an actual application where this is useful. So I only showed artificial examples of artificially rotated images, but in microscopy or aerial images, rotation invariance is more important. So here's the main takeaway again. You can replace the backbone of feature matcher to be rotation equivariant, and then your method will work better on rotated images. Right. Thanks.
Do we have any questions? We do.
How do you connect the integrated features to the
Yeah, it's basically it's a type of pooling operation. You average over the rotation equivariant features in a way to get invariant features. Yeah.
Did you try any other invariant method?
I didn't try anything. So basically what I did was using the implementation of this package, and I just specify these layers should have these properties and these layers should have these properties, and then it automatically does linear layers that satisfy this. So that will give me an average pooling. But yeah, you're right that many other pooling methods could be used to go from equivariant to invariant features. Yeah. Yeah, so a SE3 equivariant backbone would make sense if you have an input that's not an image but a volume in some sense, I think. Or if you were to make some very advanced algorithm where you sort of try to find the actual 3D positions of these points in the method itself in the early layers somehow. But I don't think it's directly applicable. No. Sorry. You mean SE3 equivariant? No, I haven't tried. I don't think it makes sense on images because they are not three-dimensional. So, but unless I might have misunderstood your question.
Thank you. This is the last talk for this block. We have one last block that is mostly about the challenge. That should be in about 25, right? So it should start in 5 minutes. I think we just take 10 extra minutes and let's meet up again in like 15 minutes here so we can do the last block of the workshop. Thank you. Now we have a coffee talk, so a coffee break. So please take some time. We should be back at 4:35 approximately. Thank you.
We are muted, yes.
Hello, everyone.
Okay, we have you. Thank you. So it's time. So we start.
Okay. Okay.
Wait, like they're not. We need to.
Yeah, sure. But I want to see the slides.
I can share my screen. Can you see my screen?
Can you please maximize?
Okay, so now I'll start my presentation.
Give it a second. Can you maximize the slides if possible?
Yeah.
Okay, perfect.
Okay. Okay. Good afternoon, everyone. Today we will present the first place solution of the IMC challenge.
Sorry, give us 1 second. Dimitra?
What? Sorry.
Okay.
Okay, sorry, we're done. We're good and restart. So this is the last block of the workshop. Now we're going to talk about the challenge presentations.
Yeah, so that's why
I forgot. So, Give us a second, sorry. So I forgot we had some slides that we wanted to go over. Can you start presenting and we'll do that first? It's going to take like 10 minutes.
Can I start now?
No, sorry. We have to go over some slides from the organizers first. Sorry, it's a mix-up.
Okay.
Yeah, it's not time yet. It's a bit chaotic. Do you want to do this or do it? Just wait. Okay, sorry. Okay. Apologies about this. So let me just do this part. So we are reintroducing the image matching challenge, which is very different from what we had the past few years. So as I said before, we moved to Kaggle, and the challenge is sponsored by Google this year, same as the last 3 years, but now with a substantial prize pool of $10,000. If you want to know more about the challenge for the previous years, you can check the live streams, which are still for the last 2 years, which were the pandemic editions of fully virtual ones, available online on YouTube. I want to just plug quickly the paper that we wrote a while ago, which was published at IJCV, which has many lessons that we learned about how to basically evaluate this entire system in a way that you can look at one number that is truly downstream and gives you an idea of how good a method, whether it's local feature or matching, is how good the method is in terms of like pose estimation, which is a bit difficult to do. We also published the open source benchmark, which has been available for a while, and we'll soon publish the ground truth. So we originally kept these private so that people had to submit local features or matches to us, and we will run the rest of the pipeline. And now we'll be able to do that yourself if you wish so. So why did we move things to Kaggle? The thing is that with self-hosting a contest, which is what we did before, we had a number of issues, right? One big one was adoption. So the previous format had very limited adoption, and specifically very few scientific papers wanted to use it. It was quite nice in the second edition because, as I mentioned at the beginning of the workshop, we had a number of like really novel research works that used it. But on the third one, we saw a drift towards just taking whatever was available and putting things together, engineering them, and trying to get good numbers, which is fine, but it's a bit of a competing objective, right? So if you are going to compete against over-engineered solutions with a simple method that has like one single contribution, you are likely not going to be like #1 on the leaderboards. And it's the issue of is this method truly state of the art, blah, 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 that makes it a bit difficult. And also ease of use, which was the opposite, right? Lack of ease of use. It was a very local feature, local matching centric. So if you wanted to do things like apply a dense method that gives you a pixel to pixel prediction for 2 images for every pixel, that was not really possible. It was kind of possible, but difficult to do. And you could not do things like direct pose estimation, right? We had some artificial categories. So for instance, we had submissions up to 2,000 key points per image, up to 8,000 key points per image. And it didn't work very well on methods like laughter, for instance, which don't have a fixed budget, right? The benchmark required a lot of manual processing because people typically send us large match files, which are pairwise, right? So you have 100 images, you have a lot more possible combinations between them, and that quickly becomes a bit intractable. Tuning was computationally expensive because it had to be done by the participants to the challenge on their own machines, and then they submitted one final solution over the test set. The whole thing required a lot of manual processing. Scoring was slow, so it's a bit annoying. And it was made significantly worse last year because we tripled the amount of data, right? So then it was a lot more tuning. The data files that we had to submit were larger. The compute It's also more costly, etc. So what does Kaggle do for you that helps you solve these problems? So there's no constraints other than compute and the dependencies. You need to submit a notebook that runs in about 9 hours, whether it's CPU or GPU, and you have to use libraries that are available, but that's about it. And we set this up as a code competition. So what you do is you just wrap your code on a Jupyter notebook. It runs over just a few images. So we publish, for instance, 3 pairs of images. And then you run it offline on data that you don't see, and then you get a score. This allows for very fast iteration, so that you can really make multiple submissions. You can work on this every day. And on our site, it gives us a lot of exposure and access to a new community. So we have actually some high scoring submissions from freelancers, people who had no previous experience working on this problem, which is, I think, pretty cool. So one thing that changed was that we simplified the challenge a lot. So we have a single data set and a single task, which is stereo. We used to have a mapping task, which was basically doing very small scale SFM, structure from motion, so 3D reconstructions, but many of them. This time, due to the difficulty to set this second task up at Kaggle, because it requires installing CalMap, it requires a lot of compute, we decided to just try to keep it simple and do just image-to-image matching, which is one of the main topic for the workshop. So that's quite fine. We use the proprietary data set.
Slides are not shared via Zoom.
They're not shared via Zoom.
I don't know why.
We don't know why.
Okay, we're stupid, that's why.
Okay. Good. Apologies. It's a complicated format. So we use the proprietary dataset, which is phone-based. It's similar to one of the datasets that we had last year. It has about 10,000 pairs of images over 100 different cities, so all over the world. And the goal is to estimate the the relative pose change between these 2 images in terms of the fundamental matrix. You estimate the fundamental matrix. And the backend at Kaggle evaluates the quality of the pose in terms of the mean average accuracy at different rotation and translation thresholds for these 2 images. You participate by, as I said, writing a simple Jupyter notebook. The competition is still open, so you can look at, it's closed, but you can still make submissions if you want. So you can look at all of the examples, you can test it out for yourself. It's quite good. There's also a lot of resources in the discussion boards, which is quite useful if you are not very familiar with this problem, and even if you are. As I said at the beginning, it worked quite well. So we increased the number of participation in terms of teams by a factor of 25 and 150 times as many submissions. What didn't work so well, I think this is the more interesting slide in this blog, because it's the lessons that we learned, is that there is a big gap in terms of a domain gap between what we call the training data and the test data, because it's just quite different. For training data, what we did was rehash one of the data sets, the largest one that we had in the previous versions of the workshop and the challenge. So this is the data set that we used since 2019, and it's quite different. So results on this training set do not necessarily translate to the test set, and we call it training, but it's not really used for training, right? It is suitable, so you have a relatively large number of images and scenes, you have depth maps, but the problem is that fine-tuning these kind of methods is really expensive. So for instance, Lofter, one of the methods that were often used in this version of the challenge, trains on 64 1018 PTIs, right? So that's just something that you don't have at Kaggle. You can have like one single GPU and with limited compute. So it's a bit difficult to try to set up something there. You have to do it on your own by downloading the data set. It's quite large, so it's a bit complicated. The evaluation thresholds are a bit loose. So you see that the results are quite high on the 0.8/1 kind of level. It was a bit short. It was a lot of work on our end. We had to make many changes to what we had last year. And that meant that we could only run it for 2 months, which I think is still pretty good, but a bit shorter than Kaggle competitions ideally run for, which would be about 3 months. And one really interesting and really annoying problem is that we still haven't decided who actually gets the monetary prizes. The way that we set this up is you can win, keep your place in the leaderboards, but due to legal reasons, you have to open source your code. And many methods, specifically the machine flip ones that Tom presented at the beginning of the workshop, since they are industry work, they are not open sourced. And some of them, like Superpoint has an open implementation, but Superglue doesn't. And people who have tried to reproduce Superglue have not been successful in reproducing the exact numbers. So it's a bit difficult, and we have to probably think of a better solution in the future to address this problem, right? Because you want people to be able to really compete and at the same time to claim the prize, which is a strong motivation to participate in this kind of contest. So the results this time is going to be very boring because they have been available since the beginning of since the end of the contest, right? Everything is public. So you can just look at the leaderboards of Kaggle if you want more details. Many solutions are published on the forums with a lot of detail, what people tried, what they didn't try, what worked, what did not work. So it's actually a lot of interesting conclusions if you want to learn more about this problem. And that's the end of this block. So now we'll have, we were going to have 5 talks. I think we'll have to drop one of them, the last one, because the speaker has some legal issues and is not able to discuss his solution with us today. So we'll have talks from the 1st, 3rd, 5th, and 7th place in the challenge, which I think is a nice combination of more engineering solutions and also some very novel works. So, sorry, this is so now we can finally, Dimitro? Sorry, I don't know how to use this. So now we can move on to the winners of the challenge. Sorry, Hongjan, for the mix-up before. Now we are actually ready for you.
Okay.
So yes.
You can share screen.
You can share your screen.
Okay. I can't share the screen.
Yes.
Okay.
I sharing. Yes, now try.
Okay. Can you see my screen now?
Yes.
Okay.
Go ahead.
Okay. Good afternoon, everyone. Today we will present the first place solution of the IMC challenge. We are Wu Shuai, Wang Chanming, Song Hongjian, and Yuki Kashiwaba. We'll first introduce our 2-stage solution, then show some ablation study results. In short, we utilize deep scan to find the co-visible area and refine the matching in these areas. And we called this method matching key points crop. Our solution is totally based on this matching key points crop algorithm. This is our pipeline. The 2 blocks represent the two stages matching respectively. In the first stage, we use Lofter and SPSG to match 2 images. To simplify, I will call the Superpoint and Superglue as SPSG in this presentation. Concatenating the key points of 2 models, we obtain the key points of stage 1. Then we use deep scan to fit these points to propose the co-visible area. We'll then generate a bounding box for each image, which represents the co-visible area, and crop along these bounding boxes to get the input images of the second stage. In stage 2, we do secondary matching with Lofter, SPSG, and DKM on the cropped area. In the end, we concatenate the key points produced by stage 1 and stage 2 to get the final key points and applied a modified ransack method in OpenCV to get the fundamental matrix. This is the output of the matching key points crop. These key points are produced by the model in stage 1. Then we apply a diff scan to cluster on those key points. The 2 boxes in each pair represents the co-visible area found by our method. In these 2 images, we can see that it does a good job of finding the co-visible region where obtained the most significant features in both images. At the same time, because we will then crop along the bounding box and only infer on the area covered by the bounding boxes, it can filter out sky, street, and moving objects, which are useless. The matching key points crop consists of 3 steps. First, we use diff scan to cluster on the matching key points of 2 images. Then with those clusters, we can get 1 bounding box for each image. Finally, we will crop the area covered by the bounding boxes. We have 2 motivations for proposing this approach. First, we want to refine the matching of the key regions. And second, we want to filter outliers appropriately. By the way, there are many clustering algorithms. Why do we choose diff scan? The first reason is that diff scan is a density-based method which fits this task well. Second, diff scan is robust to outliers. Third, we never need to specify the number of clusters before we apply a diff scan. So that's why we use it. This is the flow of this method. We will first match on both images in stage 1 and cluster on those key points. After clustering, we will have many clusters. Then we will face a problem of how to choose the cluster to generate bounding boxes. To solve it, we propose a dynamic strategy to select cluster. This dynamic selection method is based on the relative ratio of the number of matching points. In this method, the clusters are selected in the descending order of number. The selection is repeated until the ratio of the current selected cluster and the previous one is less than a threshold. For example, in the left image, the green cluster has most key points. So we first select the green one. Next, the yellow one is the second largest. So we calculate the ratio of the yellow one and the green one. The result is larger than the threshold. So we also select the yellow one. By repeating this, we select the red one and reject the pink one and the outliers. Finally, we can get a bounding box for the left image through the green, yellow, and red clusters. We find that sometimes the key points may not occur on the edges of the bounding box. In this case, if we just crop along the bounding box, you may miss some useful area. Therefore, we expand the bounding box by padding. As the right pair shows, padding the bounding box reduces the amount of wasted area and increase the public score. In our challenge solution, we multiplied a factor of 1.05 only in the horizontal direction, because our experiments have shown that vertical extensions tend to include some useless areas, such as skies and roads. Here are all the models we used in both stages. The first 4 models are for stage 1 and the rest are for stage 2. The first 4 models are used for both diff scan and getting the fundamental matrix. Matching on the co-visible area is apparently faster than matching on the whole image. So we applied a slightly larger resolution for the models in the second stage. Let's list the key of winning this challenge. The most important thing is the proposed matching key point algorithm. And second is ensemble Lofter and SPSG to get a better bounding box in the first stage. For example, the left figure is only using Lofter in stage 1, and the right one applies both Lofter and SPSG in stage 1. Both images apply the same model in stage 2. We can find that the bounding box in the right figure is obviously better than the left one, so it can get a better matching result. And ensemble both stages is also important. In fact, even only using the key points in stage 2 can get a great result. But adding the key point in stage 1 can save some wasted area by the matching key points crop method and give a better result. For example, in this pair, we can see that there are many correct matches in the right part of the right image, but they are not included by the bounding box. So if we only use the matching point of the stage 2 to calculate the fundamental matrix, we will waste all this useful information. And the multiple resolution ensemble is also useful. For example, in this image, the left one is adding the SPSG of 840 resolution to the first stage. We can capture some patterns that we missed before in the circle. And here is some ablation study results. Here is for the model. We can see that we did not apply the matching key point crop and fix the parameters of ransack. The Lofter plays best in the test data, and SPSG can give a big improve to ensemble with Lofter, and DCAM can also bring some improves. Here we can see the power of matching key points crop. Using only the key points of stage 2 could have made us ranking top 3. Using key points of both stages made us the first place. After competition, we tested different padding strategies. Surprisingly, as the last 2 rows list, adding a fixed number to pixels gets the best score. When tested on the training data, our strategy was to add padding only horizontally, because we think adding the padding vertically tends to include some unnecessary areas. However, perhaps there is a difference between the test data set and the training set. Padding on both directions are more effective for the test data in the ablation study. Thank you very much. This is all of our presentation.
Okay, thank you.
Hi.
I have actually like a question. So like you said that this DB scan is robust to outliers, and that's like question: how did you actually evaluate this, or just because it's always empirically improved performance?
Because for example, in deep scan, can you see that slide?
Mm-hmm.
Okay. In many cluster algorithms, the outliers will be added into one cluster but in deep scan, it will still remain the outliers and it will not add it into any cluster. So that's why we think it, because we want to reject the outliers, and I think so. We think this is fit this task.
Okay, thank you. Anyone from Zoom have question or from audience? Oh, okay, thank you. And I would really encourage you to try to publish this like dbScan outlier filtering approach and like compare it to like ONET and so I think it's well engineered and like first thing. Okay, we also have one more question in Zoom chat. Is super glue lighter than Lofter?
In Zoom chat, lighter than, yes, it's much lighter than Lofter. Much lighter and much faster in our experiment.
Like any other questions? Okay, then thank you again.
Okay.
Okay,
so I will stop my screen.
Yes, and I'll go to the next, which is pre-recorded video. And but I think the authors might be in Zoom to answer questions. So let's do it.
Hello everyone, this is Team Ariel. It is our pleasure to be here to show our method for the CVPR image matching challenge. This work is conducted by Jianxu, Kai Huang, Wen Sun, Gao Tongyu, Zhicheng Wang, and Ke Jianwu. And all of us come from the...
Sorry, that same stupid mistake again. And thank you for letting us know early. Share screen because I forget to do this.
Ariel.
Okay.
This is Team Ariel. It is our pleasure to be here to show our method for the CVPR image matching challenge. This work is conducted by Jianxu, Kai Huang, Wen Sun, Gao Tongyu, Zhicheng Wang, and Ke Jianwu. And all of us come from the company Ariel. We will present our work in the following parts. We will start with our solution pipeline, followed by individual modules and their corresponding results. Firstly, we will introduce our entire pipeline with this flowchart. In general, our algorithm can be divided into 4 submodules: through-point, superglue, refinement, disk, superglue, and refinement, Lofter, and DKM. Each of the baseline can achieve good performance, and we assemble them using AMS based on matching score. In adaptive augmentation, we compute transformation based on original matching result. Then we match the transformed image again and repeat adaptive augmentation after AMS, called iterative augmentation. Now, let me talk about each module. As for detector-based sub-methods, superpoint and disk use local feature refinement to improve features accuracy. This network predicts a flow from points in one image to its tentative match in the other, and corrects the position of the point according to flow. We obtain a more accurate subpixel position. Specifically, as for training glue based on disk. We use mega depth dataset with higher learning rates and stricter constraints for ground truth based on reprojection error. We also modify the loss to balance the matched and unmatched points. Finally, we got the following improved results. Once we get matched key points from our 4 methods, we fuse all of them together. The simplest ensemble strategy is direct concatenation. As shown in table, ensemble significantly improve performance. However, direct concatenation produce a lot of one-to-many wrong matches. To solve this problem, we propose match AMS to filter proximity key points based on matching score. As a result, match AMS further improve performance. Furthermore, we propose an adaptive augmentation method. Firstly, we compute the transformation based on original matching results. Then we match again based on the transformed image. Due to time constraints, we only deduct augmentation when the number of original matched key points is small. As shown in table, our iterative augmentation strategy further improves performance. To summarize, in this work, we have found that fusion of different matching methods can boost the matching result. Moreover, matching in compatibility region and adaptive augmentation significantly improve performance. Last but not least, result operation and ransack strategy also contribute to better results. This is all I have for our technical work. And let me finish this presentation with a brief introduction to our team. We are from company Ariel, who is leading the world in the revolutionary AR transformation. Ariel has made the first consumer AR glasses that are super light and easy to use. With the integration with mobile internet content ecosystem and mass production capacity, you can learn more about us on the website. Thank you for listening and feel free to ask questions.
Okay, thank you, our virtual presenters, and it seems they are not here for questions. So I'm going to the.
One is in person, that's the second one.
Sorry?
Now it's only
Yeah, Dongdi. It's a 5-place solution. So
are you checking correctly?
yeah, you can check it there. Okay.
Hello, everyone. This is a report of the 5th-place solution of image matching competition 2022. First, I will begin by giving you an overview of our pipeline. Then we will introduce related models we use in this pipeline. 2 of them are publicly available and another proposed by us. Next, we will show how each part of the pipeline works in details. Finally, we will analyze the results and show some possible solutions which may help improve the performance. Our pipeline is pretty simple. It consists of 3 parts: SPSG in red, Lofter in yellow, and EcoTR in green. In the first part, we apply SPSG on regional image pairs and get matches at 1. Then we crop the patches based on the first round SPSG and apply the second round SPSG on crop patches and get match set 2. In the second part, we use Lofter to get more accurate matches taking cropped patches as input. Next, we use ecoTR to find matches provided by SPSG in first and second round. Finally, assemble all the matches, including SPSG matches refined by ecoTR and Lofter matches, and find the fundamental matrix by MaxSet++. About the related models, like most of previous solutions, we use SPSG and Lofter as well. SPSG gives sparse matches and Lofter gives semi-dense matches. SPSG is more friendly to things with extreme wide baseline image pairs than Lofter due to the differences in attention type of transformer and search space. While semi-dense method like Lofter provides more accurate matches. We assemble two of these models and achieve far better performance than either of them. Then I'd like to have a brief introduction to our new model, ecoTR. Similar with Coulter in last year's workshop, we propose a functional query method which takes arbitrary position Q in one image as input, and the model will find its correspondence in the other image. Thanks to the end-to-end structure, our model runs dozens to 100 times faster than Coulter. As shown in the right image, two methods are tested with same resolution input and similar GPU memory cost, so that we can apply functional method into this year's computation within limited running time. Moreover, this model can cooperate with other matching models. Taking predicted matches of other model as input, ecoTR could refine the matches by fine-level transformer blocks, just like Patch2 Pixel does in its visual localization experiment. Okay, then we show the details of our method. In part 1, images are resized before fetching to SPSG. Alongside are resized to 1,600 pixels. As for two-stage matching, first, we take original image pairs as input and obtain matches at 1. Then we simply crop the patches and keep all the matches in first run SPSG inside. Next, we run SPSG in the second type of crop patches and get matches at 2. And as we can see in the top right corner, two-stage SPSG got 0.773 in test set, which scores much higher than the public SPSG baseline. In step 2, we resize the long side to 1,200 pixels for each patch cropped in previous step and keep the aspect ratio. As shown in the right image, the output are semi-dense match set 3. Moreover, Lofter gives some noisy matches, and we can see most of these matches are removed after MaxSet++. As for scores, the example of aforementioned two models, SPSG and Lofter, performed pretty well in test set, getting 0.836 higher than either of them. In step 3, we are going to show how our model ecoTR works. As mentioned above, ecoTR only refines the matches provided by SPSG. Here's an example of how refinement works. Points in red are one match pair found by SPSG. ecoTR takes the position of query and the coarse match as input and outputs the position of the refined match in orange. Apply this refinement on our pipeline as step 3 yields increase of 1% on computation. Besides, we also evaluate the refined method on YFCC dataset in line with SPSG. Results on this dataset give similar trends. It's also worth pointing out that the score can be further improved by setting virtual matches during refinement step. For each match pair found by SPSG, we set a pair of virtual matches around them. For example, refinement method without virtual matches provided 179 matches after MaxSec++, while method with virtual matches provide 351 matches. As for the score, this trick yields increase of 0.4%. We didn't apply multi-threading in this computation. More than half of running time are caused during finding fundamental metrics by MaxSec++. So the number of key points and models are limited. We believe using more key points and example of more models would achieve better performance. Besides, we simply use triple crop strategy, and we can improve it by removing noisy matches using overlap estimation method and so on. That's all. Thanks.
And I think the last speakers should be in person, if I am not mistaken. So, are you here? Yes. Great. So this is your slides. Yeah. Just in person.
Hello, everyone. I guess we're the only team presenting live here. It's great to be here. Thank you for inviting us. We are Hyokjin Kwan, Singo Bag, and Chung Moon. I'm going to be talking about our approach for Image Matching Challenge 22. So this is the overview of our pipeline. We firstly get the matching points using baseline model Lofter here, and get the extra matching points using our methods, such as warping matching or cropping matching. And then we concatenate all the matching points together and then apply radius NMS to filter out some matching points based on the score within the given radius. And then apply Wensec, in this case, VSEC, to filter out some outliers and estimate the fundamental matrix. First, for the baseline selection, there are 4 factors that we considered: is license, public universe score, precision dependency, and whether the model is detector-free or not. And there are 3 best models for candidates, but for super point, super glue combination, because they're restricted for commercial usage, so we decided not to use this model for the baseline. And the Lofter and DKM, both of them are permitted for commercial usage, and also they are position dependent and detector-free model. But the Lofter got a little bit higher public universe score in our experiment, so we chose Lofter as our baseline model. And this is the short analysis of the baseline. We firstly get the matching points using baseline model, and then we, as you see here in the bottom of the slide, there's 3 test sample pairs, and the region of interest or dense region were connected with the green lines correspondences here. But there's also non-meaningful region, such as cars, roads, or bikes, or people. There's some false positives on those regions. And also we could see that in hard cases like the 3rd image pair, the match points are spread out everywhere. And also the model just found less true positive matching points and more false positives. So we just tried to come up with some ideas to solve these problems. The first idea was k-means and cropping. So firstly, we clustered the matching points using k-means clustering algorithm, and then select the cluster that contains the most matching points and crop the image around the cluster. And we can also do the same for the other image of a pair, like this. And then we resize the cropped image and then get the matching points with the other cropped image. We found that this resizing strategy also works. And this is the comparison between original matching and cropped matching. As you can see here, we were able to cut off some uninteresting regions like cars and roads, so the model could ignore it. The next idea was warping matching. because we already saw some hard cases like the third image pair in the previous slide. The model was facing some problems with finding some meaningful matching points because the images of a pair were taken from very largely different views. So firstly, we get the matching points using baseline here as well, and calculate the homographic matrices, such as from image 1 respect to the image 2 and the other way around, or the other way around too. And firstly, we apply the homographic matrix to image 1 to warp it and resize it and get the matching points with the cropped image, resized image 2. And we also do the same to the image 2 as well and concatenate all the matching points. We found that this method was way better than just warping a single image of a pair, because in some cases, the warped image is too small or very hard to recognize. So this method improved the score. Next one is the resize trick. We found that resizing the images to bigger sizes tends to increase the number of matching points or inlier ratio. So it also helpful to improve the score, but there's some exceptions in the hard cases. So we chose 1080 for the inference size. And then there are like 4 or 5 combinations that we use for ensemble. For the model, we use Lofter and DKM, and for method, I just mentioned in the previous slides. Normally, we concatenate from number 1 to number 4, but if the number of matching points we found using number 4 was less than 500, it's too small, so we just concatenate extra matching points using the combination of k-means cropping and warping method. And then we also applied VSEC, which is the state-of-the-art RANSEC framework. We found that this is much faster than OpenCV MaxEC++, and there's tiny increase in private LB score while some decrease in public LB score. And because the default parameters of the original repository didn't work properly for the problem, so we just tried to find more right parameters and with more Python bindings. So this is the parameters that we found. And we also can see that on the table that the time spent for the inference, time spent for applying the method was much faster in VSEC, because although we used the smaller reprojection threshold for VSEC here. This is the experiment results. We can see that k-means cropping and warping method contributed the most to the leaderboard score improvement, and resizing method, radius animus method also improved the score as well. And there's confidence filtering method that I didn't mention in the previous slide that also improved the score, which is just filtering out some matching points based on the confidence given by the models like Lofter or DKM. We found this in our best private LB score case. So these are the methods that we can use for further improvement. The first one is confidence-based filtering that I just mentioned. Adaptive size cropping, because we used fixed size cropping in this competition. Maybe for better general performance, we can use adaptive size cropping. And then parallel computation to decrease the total amount of time for inference. And maybe other models like such as code tree attention, for example. For the summary, by extracting region of interest through k-means cropping, we could obtain more meaningful matching points. Also, the warping method makes it possible to cope with some edge cases where the 2 images of a pair were taken from very larger different views. And using VSEC, which is the state-of-the-art RANSEC framework, the speed was greatly improved while preserving the score. So the proposed methods such as cropping and warping boosted the score with just a couple models. I just listed up the notebooks and discussions that we forward to during the competition. We give a lot of thanks to competition organizers, Kaggle staff, and other participants for giving us this opportunity to learn and grow together. Thank you.
Thank you. Questions? Okay, in meantime, I have questions. So it seems that all solutions and you basically working, say, we have something initially good, and then we try to improve it with cropping and working and so on. And like, if this fails, nobody can like help. So have you tried to do like improve original robustness, or it's only the robustness is okay and also the precision of the like lofter is not enough? That's why you need all to do these improvements.
We actually didn't try to improve the original model. We just tried to just do some post processing.
No, I understand. I mean, like, what do you mean? Like, you improve accuracy and like not robustness. Have you tried to improve robustness by pre-processing, maybe doing like some test time augmentations? I mean, not based on cropping or matching, but like before, just before this. Like, what if you do if there are not enough key points? That's the question. Yeah.
I think the warping method was the because that was the second stage of the whole method. So if the number of matching points is too small, then we can use like the extra extra warping method or extra cropping method. So I think
Okay, thank you.
Thank you.
That's it. Okay, thank you again.
So there was one last talk, which was the solution that scored number 2, but the presenter declined to participate last minute, some unclear reasons. So we'll just move on with the last session, which is just a small wrap up. Dimitar will introduce the work.
Yes. So we have learned a lot of lessons. Actually, one thing is, okay, some of these lessons were kind of obvious before we begin, but still, like, for example, we don't have like compatible train and test set, but because of privacy issues, like this test set we used, like we only released basically 3 image pair because we cannot do this. And this is why actually I think nobody used this train test which we released. I think only one team, like from the high-performing, was using this, but not as a testing, but as a like validation approach, and they make it work somehow, but that it required some work. And then, yes, and the question is, maybe it's good, maybe it's bad, because not always you can have like huge training set. But how can approach the thing that there is test set which is comes from like very different conditions, and you cannot train on something on this, and so we don't have any answer for this, and like also it's not clear if it's necessary to actually tune model or modify, and it seems that all the participants used off-the-shelf networks which were trained on megadevs basically, and that's it. I think there is only exception was one of team which were used superglue with disk, which is basically they recreated superglue training pipeline and trained this with disk, and also on megadevs, not on other stuff. What is funny thing is like is prices and licenses. So like it's standard requirement from Kaggle, and also like from us, like that winning solution should be under like very permissive open source license like MIT or Apache 2. And because people wanted to, so and there they have a choice. Either you use superglue and have a little bit better score, or and you're not eligible unless your recreated superglue pipeline, which is, I think, so far 3 independent like reimplementations failed to have this score of superglue basically. Yes, and before, like between money and glory, like the all top team selected glory and say, okay, so we are going to be winner. We don't have any money from this because our solution not eligible, but we would be the best. And that's like what we were not expecting. I think we tried to kind of make people like use the open solutions or maybe re-implement things, but it did not happen. Okay, except that this last presented like solution, which is like so far we all reviewing all the solutions and notebooks to find out who would be actually the people who get the money, because we have to give money, but still we have problems determining who would get. Also, the thing is like, is it a correct focus to have only stereo? Like the Kaggle has its limitation. We maybe can go around it and somehow build Column, but then we can have only smaller data set. And there's question, if you have like ideal stereo model, is it good enough for all application? Should we do something to also kind of go for multi-view? Or actually, like as Tomasz Malishevich presented, or is this paradigm, okay, we are just going pairwise and let's drop this key point based approach, is going to win? And we don't know. And what we wanted actually to do is to like have different methods, like also dense methods. And actually dense methods were tested. I think this deep matching for dense matching from Prontron. It was like evaluated, but like it was not as good as Lofter. So people did, but at least they tried. Things like Demon and other like pairwise to like output the poll that they were not used. I don't know if they're like not competitive or because nobody tried. And that's still an open question. Actually, we have like 2 open questions, and maybe it's a call for like if you work at some university or company and can have some like challenging wide baseline data, which is not public yet, so nobody can fine tune. And if you would like to willing to share this data for new competition, it would be really cool. So we are open to do this. One more thing is like, okay, about this pairwise thing is it to make sense to add non-matchable pairs? Because, for example, often it's also good to have not false positive. For example, if you have like 2 pairs which not match and the correct output would be like non-match, like 0 matches. Fine, but then also it comes to a Kaggle question: how do you combine pose accuracy and basically binary classification, like match no match here? So we also have no idea about how to combine these. So if you have fresh idea, please reach us, and that's thing we are actually thinking about for the next challenge. I think that concludes our lessons learned, that is like for the next like I have no idea how to properly do hybrid format. It was like how things were like, we are stupid, but how things is because well, it's very stressful, and like there's technically there like many things need to be done differently. Like completely person is good, completely virtual is also good in a different sense, but hybrid like doesn't really work. And also for like, yeah, we have like schedule, we are over time, and we are also, I think, a little bit saved, but by a couple of video participants who actually send us not 10 minutes, but 5-minute video. Thanks to them. So, yes. Yes, we are really sorry for having like such like bad experience trying to manage something, and especially on Zoom. Then okay, the sound is not going, video is not going, and like really like we are very bad organizer. Please forgive us, and thank you to be with us here despite all this catastrophe. Yeah. And that concludes. I'd like to thank you for participation and enjoy the CVPR.
Stop it.